October 3rd, 2025. The date astronomers had marked with great anticipation for months. The day when 7 spacecraft circling Mars would direct their lenses toward the most enigmatic visitor our solar system had encountered in years. 7 orbiters, with 2 from NASA, 2 from the European Space Agency, 1 from China, and 1 from the United Arab Emirates. All were strategically positioned to capture the highest resolution imagery ever acquired of an interstellar entity. The HiRISE camera aboard NASA's Mars Reconnaissance Orbiter alone promised resolution down to 30 kilometers per pixel, 20 times sharper than anything the Hubble telescope had achieved. This was meant to be the day we finally received answers regarding 3I Atlas. Instead, it marked the beginning of the silence. 2 days prior to the flyby, on October 1st, the United States government initiated a shutdown. NASA's website displayed a stark message. The agency is closed due to a lapse in federal government funding. And when the European Space Agency eventually released images 4 days later, all that was visible was a faint, indistinct white dot traversing a backdrop of stars. 1 image from 7 spacecraft. Where were the remaining photographs? What did those cameras truly discern when 3I Atlas passed within 30 million kilometers of Mars? And why, after months of eager expectation, does it feel as though someone abruptly drew the curtains just as the grand performance was about to commence? Before we delve into what might be one of the most peculiar obfuscations in contemporary astronomy, I have a small request. Please engage the like button and subscribe if you haven't already. Then, leave a comment detailing your location, the current time there, and whether you believe NASA's silence stems from bureaucratic inertia or a more deliberate intention. And if you wish to contribute to the growth of our community, kindly share this video on Facebook, Reddit, or via your messenger. Thank you for your unwavering support. Chapter 1: The Perfect Setup. Allow me to transport you back to July 1st, 2025. The Atlas telescope in La Serena, Chile, detected an object moving at high velocity through the outer reaches of the solar system. Within hours, astronomers retrieved pre-discovery images from various archives. These images had been captured by other Atlas telescopes globally, as well as by the Zwicky Transient Facility at Palomar Observatory. The object had been photographed as early as June 14th, yet it had escaped notice until then. As its trajectory was plotted, something immediately became apparent. This entity was not orbiting the Sun, it was passing through. 3I Atlas, as it would become known, was the third confirmed interstellar object following Oumuamua in 2017 and Borisov in 2019. However, unlike its predecessors, 3I Atlas arrived with a peculiar characteristic. Its trajectory appeared almost too precise to be coincidental. Consider the plane of our solar system, the flat disk upon which all the planets revolve. Most objects originating from interstellar space approach from arbitrary angles. Oumuamua entered at an angle of 123 degrees relative to the ecliptic. Borisov approached at 44 degrees. 3 Atlas, however, came within 5 degrees of being perfectly aligned with the plane inhabited by all our planets. Avi Loeb at Harvard meticulously crunched the numbers. The probability of an interstellar object arriving within 5 degrees of the ecliptic plane purely by chance is approximately 0.2%, or 1 in 500. Now, consider this. 3I Atlas would pass within 30 million kilometers of Mars on October 3rd. It would then make a close approach to Venus. Subsequently, it would approach Jupiter in March of 2026. The combined probability of an interstellar object arriving on a trajectory that brings it into proximity with 3 major planets in sequence, solely by random chance, is a mere 0.005%, or 5 in 100,000. This begins to illuminate why some researchers express skepticism. Natural comets do not typically present themselves with such optimally aligned viewing trajectories. but the trajectory was merely the initial anomaly. As the summer progressed and more telescopes focused on 3i Atlas, accumulating data began to paint a puzzling picture. The Hubble Space Telescope captured images in late July when the object was 277 million miles from Earth. What these images revealed defied conventional expectations. When most comets are photographed, they exhibit a bright nucleus accompanied by a tail extending away from the Sun. Solar radiation and solar wind propel dust and gas backward, generating that familiar comet tail. 3i Atlas, however, presented something different. The Hubble image showed a luminous envelope, yes, but it extended forward towards the Sun rather than away. The plume of scattered sunlight stretched out ahead of the object, as if it were pushing through a medium rather than being propelled by it, and behind it, where a prominent tail would be anticipated, there was virtually nothing, merely a faint suggestion of material that only became clearly discernible in late August. Avi Loeb at UCLA processed those Hubble images. He measured the forward-facing luminescence extending several arc-seconds. Translating these angular measurements at that distance into actual dimensions revealed that the bright regions spanned thousands of kilometers. However, this is what gave astronomers pause. The extension was roughly 10 times longer than it was wide, forming an elongated teardrop shape pointing sunward. Natural outgassing from a comet nucleus typically produces more symmetrical patterns, especially when solar radiation pressure should be actively pushing material rearward. The James Webb Space Telescope observed 3i Atlas on August 6th, utilizing its near-infrared spectrograph. The Webb telescope can analyze the chemical composition of celestial bodies by examining the specific wavelengths of light they absorb or emit. What the Webb discovered was extraordinary. The gaseous envelope surrounding 3i Atlas was predominantly composed of carbon dioxide, accounting for 87% by mass. Carbon monoxide comprised approximately 9%. Water, the primary constituent of most comets we have studied, represented only 4%. Reflect on every comet humanity has observed originating from our solar system. These are typically water-rich icy bodies that formed in the frigid outer regions of the Sun's protoplanetary disk. As they approach the Sun and warm up, water ice sublimes, generating the brilliant tails we associate with comets. But 3i Atlas seemed to be constructed differently. An 87% carbon dioxide composition is virtually unprecedented. Only one other comet in our records displays a similar characteristic, Comet C 2016 R2, discovered by Pan-STARRS, which also exhibited an unusually high ratio of carbon dioxide to water. The SphereX Space Observatory, NASA's spectrophotometer for the history of the universe, Epoch of Reionization, and ICE's Explorer, observed 3i Atlas between August 7th and 15th. SphereX operates in the infrared spectrum, particularly at wavelengths around 1 micrometer, which aids in estimating object sizes by measuring the sunlight they reflect. The data collected by SphereX indicated something even more astonishing. Based on the quantity of infrared light reflecting off 3i Atlas, the nucleus could be as large as 46 kilometers in diameter. 46 kilometers. For context, 2i Borisov, the previous interstellar comet, had a nucleus estimated to be around 1 kilometer in size. 3i Atlas, if the SphereX measurements are accurate, could be 1,000,000 times more massive. 1,000,000 times. Avi Loeb published his analysis of what this discrepancy in size might imply. He calculated that at solid density, if 3i Atlas is indeed that large, we are looking at a minimum mass of 33 billion tons. This is his lower bound estimate. The object could be substantially larger. He highlighted a point that makes the statistics even more disconcerting. If interstellar objects follow a typical size distribution, we should have detected hundreds or even thousands of smaller objects before encountering something of this magnitude. The Atlas telescope system has been continuously scanning the sky for a decade. In all that time, only 3 interstellar visitors, and the third one is suddenly 1,000,000 times larger than the second. The probability curve does not support such a distribution, unless, of course, the size estimations are erroneous, unless what Sphere X detected was not the nucleus itself, but an enormous cloud of dust enveloping a much smaller core. This in turn presents its own set of challenges. If 3I Atlas possesses a dense dust coma large enough to reflect such a significant amount of infrared light, then where is its tail? Solar radiation pressure should be dispersing all that dust backward, creating a spectacular tail visible in every image. Instead, Hubble and other telescopes observed primarily forward scattering and minimal trailing material. Throughout August and September, ground-based observatories gathered additional data. The Very Large Telescope in Chile performed spectroscopy on 3I Atlas on August 25th. They detected cyanide, CN, molecules being released from the object at a rate of approximately 20 grams per second, when 3I Atlas was situated at 2.85 astronomical units from the Sun. However, what drew attention was the rapid increase in that production rate as the comet approached the Sun. The cyanide emissions scaled with heliocentric distance, raised to the power of 9.4. This is an extraordinarily steep relationship. Most comets exhibit production rates that scale with distance raised to the power of -2 to -4. 9.4 is virtually unheard of. The VLT data revealed something else unusual. They detected nickel in the gaseous plume surrounding 3I Atlas, but not iron. Nickel without iron. In nature, these two elements almost invariably appear together because they are both forged in supernova explosions and incorporated into forming solar systems in relatively consistent ratios. Finding nickel devoid of iron is akin to finding smoke without fire. It occurs in very specific industrial processes involving the manufacture of nickel alloys, but in naturally occurring space objects, it is anomalous. Then, in early September, amateur astrophotographers Michael Jagger and Gerald Raymond captured images of 3I Atlas during a total lunar eclipse. Their photographs revealed something unexpected. The comet, which had appeared reddish in all previous spectroscopic studies, now glowed green. Green comets are not uncommon. This coloration typically originates from diatomic carbon molecules, C2, which fluoresce green when energized by solar ultraviolet light. But here lies the problem. Earlier spectroscopic observations by Luis Salazar Manzano's team at the University of Michigan indicated that 3I Atlas showed extreme depletion of carbon chains. The comet possessed significantly lower levels of C2 and C3 molecules than any other recorded comet. If 3I Atlas lacks diatomic carbon, what is causing the green luminescence? One possibility is the steep increase in cyanide production detected by the VLT. Cyanide can produce greenish emissions under certain conditions, but again, the chemistry does not quite align. The combination of high carbon dioxide, low water content, depleted carbon chains, abundant cyanide, nickel without iron, and now a green glow that should not be present based on this molecular inventory. It paints a picture of an object that stubbornly refuses to fit any established template for natural comets. By late September, 3 Atlas had moved sufficiently close to the Sun that observing it from Earth became challenging. The celestial geometry placed the comet near the Sun's position in our sky, rendering it invisible against the solar glare. From Earth-based telescopes, 3I Atlas effectively vanished into the overwhelming brightness. This is where Mars assumed critical importance. Mars is considerably farther from Earth than the Moon. However, in early October of 2025, Mars occupied a position in its orbit that afforded the spacecraft orbiting the red planet a significantly better vantage point for observing 3I Atlas. As Earth lost its line of sight, Mars gained one. 7 orbiters circled Mars, each equipped with cameras and spectrometers primarily designed for studying the Martian surface, but capable of being repurposed for specialized observations. NASA's Mars Reconnaissance Orbiter carried the high-resolution imaging science experiment, HiRISE camera, arguably the most powerful camera ever sent to another planet. From its orbital altitude around Mars, HiRISE can resolve features down to 30 centimeters. When directed at 3i Atlas during its closest approach, HiRISE's angular resolution translated to approximately 30 kilometers per pixel. This represents a resolution 20 times superior to what Hubble achieved when imaging the object in July. NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, carried the imaging ultraviolet spectrograph, capable of analyzing ultraviolet emissions from 3i Atlas and mapping the distribution of gases in its coma. The European Space Agency's Mars Express orbiter was equipped with the high-resolution stereo camera, along with the Omega and SPICAM spectrometers for compositional analysis. ESA's ExoMars Trace Gas Orbiter featured the Color and Stereo Surface Imaging System, CASIS, along with the NOMAD spectrometer and an infrared instrument. China's Tianwen-1 orbiter contributed the moderate-resolution imaging camera. The UAE's HOPE orbiter carried the Emirates Exploration Imager and 2 spectrometers, EMIRS and EXAL. 7 spacecraft, multiple cameras, multiple spectrometers, all positioned to gather data during 3i Atlas's closest approach to Mars on October 3rd. Astronomers worldwide anticipated this would provide the most detailed view yet of the interstellar visitor. The pieces were in place, the timing was perfect, the instruments were ready, and then, 2 days before the event, the United States federal government initiated a shutdown. Chapter 2: The Silence Protocol. When a government shutdown occurs, certain agencies cease operations while others maintain minimal staffing for essential functions. NASA typically places around 80% of its workforce on furlough during these periods. Public affairs offices close, social media becomes inactive, the primary website displays the standard notification regarding lapsed funding. However, mission-critical operations continue. The Mars orbiters do not cease functioning. The instruments do not power down. Data continues to flow from spacecraft to ground stations, is recorded, and is stored. What changes is the pathway for public dissemination. NASA's raw image archives for Mars missions normally update continuously. The Perseverance rover, for example, uploads images from its various cameras to a public server where anyone can access them. During normal operations, these raw images appear within hours of being captured, sometimes even faster. The system is largely automated, but processing those raw images into calibrated, analyzed, and publication-ready formats requires human expertise. It necessitates scientists examining the data, correcting for instrumental artifacts, stacking multiple exposures if required, and preparing explanatory materials for public understanding. On October 1st, 2025, this human expertise was furloughed. Over 15,000 NASA employees received layoff notices. The timing meant that when 3i Atlas made its closest approach to Mars on October 3rd, the individuals who would normally process and release spacecraft imagery were at home, technically prohibited from performing official duties. The European Space Agency, not subject to United States funding politics, continued its operations as usual. ESA's Mars Express and ExoMars Trace Gas Orbiter both observed 3i Atlas as planned between October 1st and 7th. These spacecraft directed their cameras toward the interstellar visitor. The ExoMars TGO utilized its CASIS camera to capture a series of 5-second exposures. Mars Express attempted observations with its high-resolution stereo camera, although the exposure time of half a second proved insufficient for detecting such a faint distant target. On October 7th, 4 days after the Mars flyby, ESA publicly released the CASIS images. The scientific community and space enthusiasts who had been awaiting them with keen anticipation finally had something to examine. What they saw was a blurry white dot moving across a star field. The background stars appeared as streaks, because CASIS tracked the moving comet during the exposure. 3i Atlas itself appeared as a slightly elongated blob, bright at the centre and diffuse at the edges. The images confirm the existence of 3i Atlas and its flyby of Mars as predicted, but they revealed little about its structural composition. Nick Thomas, principal investigator for the CASSIS instrument, explained the challenges. CASSIS was designed to photograph the bright surface of Mars from a distance of just a few hundred to a few thousand kilometers. Directing it at a faint object 30 million kilometers away pushed the instrument far beyond its intended operational parameters. The comet appeared roughly 10,000 to 100,000 times fainter than typical targets. The fact that CASSIS detected anything at all demonstrated impressive versatility, but the resolution was inherently limited. Avi Loeb analysed the CASSIS images in detail. He noted that the width of the bright luminescence around 3I Atlas in those pictures measured approximately twice the diameter of background stars within the same frame. Given the angular resolution of CASSIS, this translated to roughly 680 kilometers of visible coma. This is an order of magnitude smaller than what Hubble had observed. However, Hubble benefited from significantly longer exposure times and a much larger aperture. CASSIS could only detect the brightest central region, missing the fainter outer envelope that extended much farther. The noteworthy detail Loeb pointed out was that the extent of scattered light around 3I Atlas appeared qualitatively similar to what Hubble had captured back in July, just compressed into a smaller apparent size due to instrumental constraints. The data suggested no substantial increase in outgassing had occurred over the intervening months. If 3I Atlas were a typical comet approaching the Sun, one would expect its activity to escalate dramatically as solar heating intensified. The relatively stable appearance implied either that the object was not responding to solar heating in the manner of ordinary comets, or that its response was more subtle than anticipated. Meanwhile, speculation regarding NASA's images intensified. 7 spacecraft had been in position. The Mars Reconnaissance Orbiter's HiRISE camera should have provided exceptionally detailed views. MAVEN's ultraviolet spectrograph should have mapped the gas distribution. Yet nothing materialized in the public archives. The automated raw image feeds from the Perseverance rover continued to update, displaying the usual surface geology of Jezero crater, but no official processed images of 3I Atlas appeared. On October 4th, just one day after the flyby, something emerged in the Perseverance raw image archive that captured attention. The right navigation camera, one of the rover's nav cams used primarily for surface navigation, had captured an image at 21:33 local solar time on Mars. The image displayed an elongated streak of light against the dark sky. The timestamp coincided with the period when 3I Atlas would have been visible from Mars. Amateur astronomers immediately began downloading and analysing the image. Simeon Schlosser, an astrophotographer who regularly processes publicly available space mission data, stacked multiple navcam frames together to enhance faint details. He identified what appeared to be a smudge of light in the constellation Corona Borealis, close to where orbital calculations predicted 3I Atlas should be located. Stephen Burns created a 9-minute time-lapse sequence by stitching together sequential navcam images, revealing a bright object moving across the Martian sky. However, the morphology of that streak raised questions. The object in the navcam composite appeared roughly 4 times longer than it was wide, presenting a cylindrical or cigar-like appearance. Social media erupted with comparisons. Some noted its resemblance to the Doomsday Machine from the 1960s Star Trek episode, a colossal cylinder that consumed planets. Others pointed out the similarity to Oumuamua, which had also exhibited an elongated shape, although Oumuamua's length-to-width ratio was closer to 10:1, based on its light curve variations. Was 3I Atlas truly cylindrical, or was some other phenomenon creating that appearance? Avi Loeb addressed this question in a detailed analysis. He calculated that the navcam image was likely a composite stack of hundreds of individual frames taken over approximately 10 minutes. During that interval, 3I Atlas would have been traversing the Martian sky at a significant apparent velocity. Mars orbits the Sun at 24 kilometers per second. 3I Atlas was travelling at 67 kilometers per second relative to the Sun in a retrograde direction, opposite to Mars's motion. The relative motion between the celestial wanderer and Mars resulted in an approximate path distance of 50,000 kilometers over a 10-minute observation interval. Should amateur sky gazers combine all those acquired frames without factoring in the object's movement, they would generate a luminous trail. The extent of this trail would be contingent on the duration of the image compositing process, not on the actual physical dimensions. 3 individual snapshots, as well as NavCam's maximum exposure capability of 3 28/100ths of a second, would depict 3 Atlas as a predominantly spherical dot. Merging them creates the illusion of elongation. Consider it akin to photographing a vehicle traversing a nocturnal highway with an extended exposure setting. The vehicle itself may be compact, but in your photograph it appears as a prolonged streak of light. This streak does not represent the vehicle's actual form, but rather its displacement during the exposure. The identical principle applies here. The elongated appearance in the imagery processed by amateur enthusiasts likely stems from motion blur, rather than 3-eye Atlas being physically stretched out. Nevertheless, NASA had not provided confirmation as to whether the NavCam images even depicted 3-eye Atlas. The agency maintained silence. The prominently featured image of the week on NASA's Mars Reconnaissance Orbiter webpage, for the period spanning September 28 through October 4th, included a NavCam image from the Perseverance rover, yet no accompanying explanation identified the bright celestial body. Given the government shutdown and the reduced public affairs personnel, perhaps that silence was understandable, but the absence of clarity allowed conjecture to flourish. Subsequent to this, reports emerged, unverified but circulating within enthusiast circles, that NASA had conducted preliminary briefings with select mainstream media organizations on October 4th, a mere 24 hours after the close encounter. These briefings allegedly characterized 3 Atlas as a commonplace comet, without addressing any of the peculiar characteristics that had perplexed astronomers. No supporting scientific documents accompanied these briefings. No visual evidence was disseminated, only verbal assurances that all was normal. Dr. Michael Salla, who manages the Exopolitics website and has dedicated decades to scrutinizing governmental secrecy surrounding space-related matters, identified a recurring pattern. He traced the historical approach NASA takes with potentially contentious imagery back to 2 individuals who came forward in 2001, Donna Hare, who worked as a technical illustrator for NASA contractor Philco Ford, and Carl Wolf, a sergeant in the United States Air Force possessing top-secret crypto clearance. Both provided testimony at the Disclosure Project press conference organised by Dr. Stephen Greer. Hare detailed her work at the Lunar Receiving Laboratory at the Johnson Space Center, where she held security clearance to access certain zones. She testified that she witnessed NASA Photolab technicians airbrushing anomalies from lunar photographs prior to their public release. She communicated with multiple agency insiders who corroborated this as standard practice. Wolf recounted his experience at Langley Air Force Base, working with photographic equipment used to process imagery from the lunar orbiter missions. He claimed to have seen photographic evidence of artificial structures on the far side of the Moon, evidence that was classified and removed from public versions of the imagery. Regardless of whether one subscribes to these accounts, they established a precedent for what Salah terms scrubbing, the systematic exclusion of potentially controversial elements from space imagery before its public dissemination. This technique has evolved over time. In the nascent stages of Mars exploration, orbiters transmitted live feeds that anyone monitoring the appropriate radio frequencies could access. When discrepancies appeared in these live feeds, word spread rapidly through amateur radio communities. NASA's response was to discontinue live feeds and transition to delayed releases with built-in processing time. The International Space Station occasionally broadcast live video footage of Earth from its external cameras. On multiple occasions over the years, viewers have reported observing objects in these feeds that defy easy explanation. Strange lights, structured forms moving in unconventional patterns. Whenever such objects materialize, the feed is abruptly cut to a colored screen or switched to a different camera angle. NASA typically attributes these interruptions to signal loss or routine camera adjustments, but the timing often coincides suspiciously with whatever anomaly the viewers were observing. Mars missions followed a comparable progression. Early missions made imagery available promptly, often within hours. However, as public interest grew and image analysis tools became more sophisticated, NASA instituted additional review stages. Images now undergo calibration processes, artifact removal, quality assessments, and editorial review before public release. These steps serve legitimate scientific objectives. Raw spacecraft data can be prone to noise, may contain instrumental errors, and can be misinterpreted without appropriate context. However, they also establish a buffer period during which problematic imagery can be identified and handled differently. Michael Salla posited that the present circumstances surrounding 3 Atlas align with this established pattern. 7 spacecraft captured images of the object. At least some of these spacecraft, particularly the Mars Reconnaissance Orbiter with its potent high-resolution camera, must have acquired clear, detailed images. The absence of these images in the public record, even as automated raw data streams continue from other instruments, suggests a deliberate decision was made regarding what to release and what to retain. Consider the sequence of events. October 1st, the government shutdown commences. October 3rd, 3I Atlas makes its closest approach to Mars. October 7th, the European Space Agency releases blurry images from its CAS instrument. October 8th, 9th, 10th, 11th, 12th. NASA remains silent. No processed images, no technical reports, no scientific papers analysing the Mars flyby data. A complete lack of communication. Evie offered commentary on the situation during an interview with NBC News. He directly addressed the question of whether the government shutdown represented some form of conspiracy to conceal information about 3 Atlas. His response was characteristically understated. The delay, he stated, is not indicative of extraterrestrial intelligence. It is more a symptom of terrestrial incompetence. He acknowledged the frustration but attributed the silence to bureaucratic inefficiency rather than intentional obfuscation. Perhaps that assessment is accurate. Perhaps the silence truly stems from furloughed employees and stalled workflows. However, the timing remains noteworthy. Following months of anticipation, after the precise positioning of multiple spacecraft, after the astronomical community had marked October 3rd as the date when definitive answers about this peculiar visitor would finally be obtained, the curtain fell at the very moment the performance was scheduled to begin. And that pattern, whether deliberate or coincidental, contributes to a long-standing history of reticence surrounding space missions. The public desires openness. Scientists require data. Yet, institutional inertia, classification protocols and image processing pipelines create impediments where information enters but does not always exit, at least not promptly, and sometimes not at all. Chapter 3. Behind the Sun. October 29th, 2025, approaches. This date holds significance as it marks perihelion, the point at which 3I Atlas achieves its closest proximity to the Sun, 1 3600ths of an astronomical unit, approximately 203 million kilometers, positioning the comet just within Mars's orbit. For observers on Earth, this creates a geometric challenge. 3I Atlas will be situated almost directly behind the Sun from our vantage point, obscured by solar glare, rendering it entirely unobservable from ground-based telescopes. This period of invisibility extends from late October through the majority of November. Terrestrial astronomers lose visual contact with the interstellar visitor precisely when it should be at its most active. Solar heating intensifies dramatically as celestial bodies approach perihelion. Comets typically exhibit peak outgassing during this phase, their ices sublimating rapidly under intense radiation. If 3I Atlas is indeed a natural comet, perihelion should precipitate spectacular activity. Luminous jets of gas and dust, potentially even fragmentation, if thermal stress surpasses structural integrity. However, We will be unable to witness this from Earth. The sun completely obstructs our view. This is not unusual. Comets regularly pass behind the sun, and astronomers simply await their reappearance on the opposite side. What distinguishes this circumstance is the multitude of questions already surrounding 3I Atlas. Its anomalous chemistry, its unusual trajectory, the missing Mars flyby imagery, all combine to create a scenario where the object vanishes from observation at the most crucial juncture. Avi highlighted the implications in one of his October blog posts. If 3I Atlas is a natural comet, perihelion might cause it to fracture. Thermal stress and tidal forces exerted by the sun's gravity can disintegrate fragile icy bodies. Comet Shoemaker-Levy 9 famously fragmented when it ventured too close to Jupiter in 1992, torn apart by tidal forces before the fragments impacted the gas giant. Other comets have disintegrated upon approaching the sun, unable to withstand the heat. Jets of sublimating gas can also induce rotation in a comet. If outgassing is unevenly distributed across the surface, it generates torque, acting like miniature thrusters that accelerate the nucleus. Rapid rotation introduces centrifugal forces. Comet 32, P. Julia Farr, broke apart in 2016, likely due to rapid spinning triggered by asymmetrical outgassing. If 3I Atlas fragments at perihelion, Earth-based observers will witness multiple pieces emerging in early December instead of a single cohesive entity. However, Lowe also outlined an alternative possibility. If 3I Atlas is technological, if the object is a spacecraft rather than a natural comet, perihelion presents a unique opportunity. Concealed behind the sun from Earth's perspective, the object could maneuver undetected. It could utilize solar gravity for a gravitational assist, altering its trajectory in ways impossible for a passive celestial body. It could deploy smaller craft, miniature probes that detach from the main body and adopt different orbits. The retrograde trajectory becomes significant in this context. 3I Atlas moves in opposition to the direction in which planets orbit the sun. From the object's frame of reference, planets are approaching it rather than receding. This geometry simplifies trajectory calculations for interception. A probe released from 3 Atlas with velocity partly counteracting the main body's motion could decelerate relative to the sun, settling into a bound orbit rather than continuing on a hyperbolic escape path. These probes could then await, positioned along orbital paths where they would eventually intersect Earth, Venus, or Mars as those planets continue their circuits around the sun. Imagine dropping breadcrumbs along a hiking trail. You do not need to aim each crumb at a specific destination. You simply need to place them along the route you know hikers will follow. The retrograde orbit of 3I Atlas means that any released probes would naturally intersect planetary orbits simply by reducing their velocity relative to the sun. The timing would depend on when and where the releases occurred, but the geometric configuration favors eventual encounters. This scenario presumes intent, assumes technological capability, and postulates a level of sophistication that most scientists would find difficult to accept. However, Lowe has consistently explored low-probability possibilities when they remain consistent with available data. He rates 3I Atlas as 6 out of 10 on what he terms the low scale, where 0 signifies a definitively natural object and 10 represents a definitively artificial one. 6 indicates genuine uncertainty, with sufficient anomalies to warrant serious consideration, but not enough evidence for definitive conclusions. Michael Salla elaborated on this theme through his Exopolitics platform, presenting 11 distinct theoretical frameworks for interpreting 3I Atlas. These range from entirely natural explanations, such as a large comet with unusual chemical composition, to various technological scenarios, an extraterrestrial reconnaissance probe, an abandoned generation ship, a deliberately dispatched contact vessel, a hostile weapon system. Salla does not endorse any single interpretation, but contends that institutional science prematurely dismisses possibilities without comprehensive investigation. One of Salah's more intriguing suggestions involves what he terms the white hat hypothesis. Within this framework, 3 Atlas represents a collaborative endeavour between benevolent extraterrestrial civilizations and reform-minded factions within Earth's military and intelligence communities. The object purportedly emits frequency codes, energetic patterns that influence consciousness and accelerate spiritual enlightenment. The timing of its arrival, Salah argues, aligns with increasing disclosure efforts, a rise in whistleblowers, and growing public awareness of classified projects. Such speculation undeniably extends far beyond the purview of mainstream scientific discourse. It blends ufology, consciousness studies, geopolitics, and fringe physics into a narrative that most academics would summarily reject. However, Salah has cultivated a following over decades by documenting patterns of governmental secrecy, tracking whistleblower testimonies, and proposing frameworks that attempt to make sense of seemingly disparate anomalous phenomena. Whether these frameworks accurately reflect reality or represent elaborate attempts to impose patterns on random data remains a subject of intense debate. What is undeniable is that deficiencies in official information create fertile ground for speculation to thrive. When NASA fails to release anticipated imagery, when agencies fall silent during crucial observation windows, when data that should be publicly accessible remains withheld, individuals naturally construct explanations to fill these voids. The perihelion passage introduces another facet to this dynamic. From late October through most of November, no Earth-based telescope can observe 3I Atlas. The object resides in a blind spot concealed behind 200 million kilometers of solar plasma. Space-based observatories positioned at different angles might maintain a line of sight, but these missions have their own targeting constraints and data release schedules. The European Space Agency's Jupiter Icy Moons Explorer, the JUICE mission, finds itself in an advantageous position. JUICE launched in April 2023 and is currently en route to Jupiter via a complex trajectory involving multiple gravitational assists. In November 2025, JUICE will be positioned such that 3I Atlas becomes visible from its perspective, and the comet will have just passed perihelion, potentially exhibiting its peak activity. Between November 2nd and 25th, JUICE will observe 3I Atlas utilizing several instruments. The Janus camera system is capable of capturing optical images. The MARSIS spectrometer maps composition across visible and infrared wavelengths. The UVS ultraviolet spectrograph analyzes gas emissions. The PET particle detector measures the interaction between the solar wind and the comet's outgassing. This multi-instrument approach should yield comprehensive data regarding 3I Atlas's behavior during its most active phase. However, there is a caveat. JUICE currently operates within a communicationally restricted environment. The spacecraft is situated close to the Sun from Earth's perspective, utilizing its high-gain antenna as a heat shield. Communication relies on the medium-gain antenna, which transmits data at considerably slower rates. Furthermore, JUICE is positioned on the far side of the Sun relative to Earth, meaning signals must traverse a greater distance through the solar system. The combination of these factors implies that data from the November observations will not reach Earth for several months. ESA estimates that JUICE's data from the 3I Atlas observations will not be available for analysis until February 2026, 3 months after the observations. For 3 months, during which the scientific community and the interested public will remain without any information about what transpired at perihelion. 3I Atlas will emerge from behind the Sun in early December, once again visible from Earth-based telescopes, but the critical perihelion period will remain an enigma until the JUICE data becomes accessible. Then there is the Juno spacecraft, NASA's mission currently orbiting Jupiter. Juno arrived at the gas giant in July 2016 and has been studying Jupiter's atmosphere, magnetic field, and gravitational structure ever since. The mission has been extended multiple times, with operations continuing through at least September 2025. In theory, Juno could observe 3I Atlas as the comet passes through Jupiter's vicinity in March 2026. However, NASA deactivated Juno's cameras. The Juno Cam, a visible light imager primarily intended for public outreach, was switched off in September 2025, mere weeks before 3I Atlas would enter Juno's observable region. The official explanation cited power budget constraints and the necessity of prioritizing scientific instruments. Juno Cam was always considered a supplementary instrument, not integral to the core mission objectives. Deactivating it to conserve power for other systems makes operational sense. But the timing strikes some observers as suspicious. Juno could have provided close-range imagery of 3I Atlas during its Jupiter flyby, offering perspectives unattainable from any other spacecraft. Instead, the cameras fall dark just as the opportunity arises. Coincidence or coordination? Depending on your prior assumptions regarding institutional transparency, one might interpret this differently. What is objectively true is that 3I Atlas enters a series of observational gaps precisely when it should be most intriguing. Earth-based telescopes lose sight in late October. Juno's cameras are offline. JUICE captures data but will not transmit it until February. The Mars orbiters that could have provided detailed imagery in early October remain silent, their data either unreleased or possibly restricted. The outcome is a months-long blackout period during which our most enigmatic interstellar visitor in years operates beyond scrutiny. If 3I Atlas behaves precisely as 2 Borisov did during its 2019 perihelion passage, exhibiting typical cometary activity, fragmenting naturally, or remaining intact and continuing on its hyperbolic trajectory without deviation, then the speculation will appear excessive in retrospect. However, if 3I Atlas does something unexpected, if it maneuvers, if it deploys objects, if its trajectory shifts in ways inexplicable by outgassing or gravitational interactions, we will not know until after the fact. And even then, without continuous observational data, distinguishing between what occurred naturally and what might have been deliberate becomes nearly impossible. This uncertainty extends to ground-based observers as well. Amateur astronomers equipped with telescopes in the 8-inch diameter range or larger should be capable of spotting 3I Atlas when it emerges from solar glare in early December. The comet's predicted brightness, approximately magnitude 10, places it within the reach of serious amateur equipment. Networks of amateur observers will undoubtedly direct their instruments skyward, eager to capture images after the extended blackout period. However, what they observe will represent the aftermath, not the event itself. If 3I Atlas fragmented at perihelion, they will detect multiple pieces. If it remained intact, they will track a single object. If it maneuvered, they might notice the trajectory deviating from predictions. But reconstructing precisely what transpired during the unobserved period necessitates inference, orbital mechanics calculations, and comparative analysis with pre-perihelion data. The direct observational record will possess a void that no amount of post-analysis can completely fill. This brings us back to the question of institutional responsibility. When governmental bodies such as NASA possess capabilities that are beyond the reach of ordinary individuals and even most scholastic establishments, these entities inevitably become custodians of information. Should they disseminate their findings promptly and with complete transparency, the collective body of scientific minds and the public at large can engage in a shared evaluation of the evidence. Conversely, if they opt for delays, impose restrictions on access, or selectively release information, they foster information disparities that breed distrust. Chapter 4 delves into the challenge of scale. Let us revisit a matter that warrants greater scrutiny than it initially receives. The estimations of the mass of 3I 2019 U1, Oumuamua, diverge so significantly, contingent upon the specific instrumentation and measurement methodologies employed, that harmonizing these figures presents a formidable challenge in itself. This is not merely an exercise in pedantic calculation. The mass of Oumuamua directly influences every subsequent conclusion we draw regarding its fundamental characteristics. Consider the initial observations obtained by terrestrial telescopes. Upon their first detection of Oumuamua in July, astronomers calculated its luminosity and, by applying conventional assumptions about its reflectivity, estimated its size. If one presumes an object possesses an albedo, meaning a reflectivity of 0.05, a figure typical for cometary nuclei, one can deduce its requisite size by working backward from the quantity of light it reflects. These preliminary assessments suggested a diameter ranging from 10 to 20 kilometers. Subsequently, the Hubble Space Telescope observed Oumuamua on July 21st. The images revealed a diffuse luminosity extending for several arc-seconds. However, discerning the precise dimensions of the nucleus from this glow proved intricate. The comas of comets, which are the envelopes of gas and dust enveloping the nucleus, can substantially exceed the size of the solid core. Hubble's resolving power limited the precision with which astronomers could delineate the boundary between the nucleus and its surrounding coma. By August 20th, following supplementary observations, the Hubble data indicated a nucleus diameter falling somewhere between 440 meters and 5.6 kilometers. This represents an upper bound of 5.6 kilometers, implying the actual size could be any value within that interval. 5.6 kilometers at the upper extreme, but recall the measurements obtained by SPHERE. The infrared observations conducted in mid-August suggested a diameter of 46 kilometers, not 5.6. 46 kilometers, an object nearly 9 times larger in diameter, translating to approximately 700 times greater in mass, assuming comparable density. Love explored potential explanations for this disparity. One hypothesis posits that the SPHERE measurements captured reflected sunlight not from the nucleus itself, but from an immense dust cloud. If Oumuamua is enveloped by a vast cloud of dust particles, individually microscopic yet collectively expansive, they could reflect sufficient infrared light to give the entire system an apparent size of 46 kilometers. Nevertheless, this explanation engenders the issue we previously touched upon. Where is the tail? The pressure exerted by solar radiation propels dust particles away from the sun. A dust cloud of sufficient magnitude to mimic a 46-kilometer nucleus would invariably produce a spectacular tail, readily discernible in all optical imagery. Yet, the majority of observations indicate minimal tail development. The alternative explanation, the one that creates statistical discomfort, is that the nucleus is indeed that large. If the solid core of 3I Oumuamua measures 46 kilometers in diameter, and if we posit a density approximating solid ice, around 1 gram per cubic centimeter, the mathematical calculation yields a mass exceeding 33 billion tons. Lowe calculated this figure as a minimum. If the density is higher, or if the object incorporates a substantial proportion of rocky material mingled with ice, its mass could be considerably greater. Now, consider the statistics of discovery. The Oumuamua telescope network has been systematically surveying the heavens for over a decade, with a specific focus on near-Earth objects and other transient phenomena. Throughout this entire period, we have detected precisely 3 interstellar entities. One, Oumuamua, measured approximately 100 meters in diameter, roughly the size of a football field. A second, 2I Borisov, measured around 1 kilometer. And then, 3 Oumuamua, potentially 46 kilometers. This represents a 46-fold increase in size, equating to roughly a 1,000,000-fold augmentation in mass. In natural systems, size distributions typically adhere to power law relationships. Smaller entities are exponentially more prevalent than their larger counterparts. This principle holds true for asteroids, comets, planets, and stars alike. If one surveys a population and ascertains its size distribution, one should anticipate encountering numerous small objects for every large one. While the precise ratio may vary depending on the specific population, the underlying pattern remains remarkably consistent across diverse astronomical contexts. Should interstellar objects conform to a similar distribution, we would expect to have detected hundreds or even thousands of kilometre-sized objects akin to Borisov, before encountering an object of Oumuamua's potential 46-kilometre scale. The probability of observing the sequence we have actually recorded, one diminutive object, followed by one of moderate size and then immediately a colossal one, does not align with any plausible size distribution model. This is unless the observations are erroneous, unless 3i Oumuamua is not truly 46 kilometers in size, or unless the infrared measurements have misinterpreted some aspect of the object's characteristics or geometry. This brings us back to the fundamental question of precisely what is reflecting that infrared radiation. One proposition suggests that 3i Oumuamua might be a rubble pile, a loosely aggregated collection of smaller fragments rather than a singular cohesive nucleus. Rubble pile structures are commonly observed among asteroids and certain comets. They form when gravitational forces bind fragments together without their fully coalescing into solid rock. The interstitial spaces between these fragments create internal voids. When a rubble pile comet approaches the Sun, solar heating can vaporize ices deep within its structure, generating internal pressure that compels gas to escape through surface vents. If Oumuamua is a rubble pile with a highly porous internal architecture, its apparent size could be substantial, while its mass remains comparatively modest. Envision a solid snowball juxtaposed with an equal volume of loosely packed snow. The snowball is dense and compact. The loose snow occupies the same spatial extent, but contains significantly more empty space and considerably less actual material. A 46-kilometre rubble pile could possess a mass comparable to a 10-kilometre solid nucleus, provided its bulk density is sufficiently low. However, rubble pile structures also influence how these objects respond to thermal stress. The internal voids offer insulation, impeding efficient heat penetration. Outgassing can become more vigorous, as pressure builds internally before finding avenues for escape. The observable signatures distinguishing a rubble pile from a solid nucleus differ in subtle yet measurable ways. Spectroscopic analyses of gas production rates, patterns of thermal emission, and changes in rotational state all provide valuable insights into internal structure. To date, the observations of 3i Oumuamua have not definitively favoured either interpretation. The accelerated production of cyanide as the comet neared the Sun suggests a temperature-dependent chemical process. However, whether this points to a solid or a rubble pile structure remains equivocal. Its unusual chemical composition, characterized by a predominance of carbon dioxide and a low water content, could stem from its formation in an exceptionally frigid region of a distant protoplanetary disk. Alternatively, it might indicate significant alteration due to prolonged exposure to cosmic rays during its interstellar transit, or through some other mechanism. There exists another perspective to contemplate. What if Oumuamua comprises a solid core surrounded by a far more extensive yet tenuous cloud of material? This would not be a conventional coma of gas and dust, but rather something more structurally defined. Certain comets exhibit formations known as dust trails, which are streams of larger particles that disperse along the comet's orbital path. These trails can extend for millions of kilometers, yet remain sufficiently diffuse to preclude the formation of visible tails in the conventional sense. If Oumuamua is shedding material in a distinct pattern, perhaps generating an envelope of particles that accompanies the nucleus, that envelope could reflect infrared light in a manner that makes the entire system appear larger than the core actually is. The inherent difficulty with all these proposed explanations is that they are formulated retrospectively to reconcile the observed data. We witness something anomalous, and subsequently devise hypotheses that might account for it. Yet, in the absence of high-resolution spatial imaging, without the capacity to visually scrutinize the very structures we theorize about, differentiating between competing models becomes a formidable task. The flyby of Mars in early October was anticipated to provide that critical spatial resolution. HiRISE stated that a capability of 30 km per pixel would have resolved a 46-kilometre object as a distinct disk rather than a mere point source. We would have observed structural details, perhaps even surface features, had the resolution been adequate. However, we do not possess those images, or rather, they presumably exist within NASA's data archives but have not been made public. The European imagery from Cassini lacks the necessary resolution to definitively address the question of size. Consequently, we are left with this pervasive uncertainty. A ninefold disparity between the lower and upper estimates, a difference that profoundly alters the statistical implications and the physical interpretation of what 3i Oumuamua represents. Lowe addressed this uncertainty in his public lectures and written works. He underscored that the size determination derived from forthcoming observations, particularly if NASA eventually releases the high-resolution data, will be paramount in assessing whether Oumuamua aligns with natural population models. If the nucleus is diminutive, under 10 kilometers, the statistical argument weakens. We could then interpret Oumuamua as an exceptionally luminous comet with peculiar chemistry, yet fundamentally natural. If, however, the nucleus is substantial, approaching the 46-kilometer estimate, the statistical argument gains strength. Such an object becomes more challenging to explain as a random occurrence within natural populations of interstellar comets. This connects back to the broader inquiry concerning the prevalence of interstellar objects. Prior to Oumuamua, theoretical projections existed, but observational constraints were absent. The detection of 3 interstellar objects within an 8-year span provides a rudimentary estimate of their spatial density. Based on this detection rate, and taking into account survey limitations, astronomers calculate that there might be a single interstellar object within Earth's orbit at any given moment. As we extend our reach further from the Sun, this density increases. At Neptune's orbital distance, there could be dozens. Within the Oort cloud, thousands. These estimations are contingent upon assumptions regarding size distributions. If the majority of interstellar objects are small, their spatial density could be higher. Conversely, if they are predominantly large, the density must be lower to reconcile with the observed detection rate. The statistics form a web of constraints. Alter one assumption, and others must be adjusted to maintain consistency with empirical observations. Oumuamua places particular strain on this constraint web precisely due to its size ambiguity. A 46-kilometer interstellar object should not be the third such entity we encounter. Statistically, we ought to discover smaller objects first in abundance, before having the extraordinary good fortune to detect a giant. The fact that we may have identified a giant as our third detection suggests either extraordinary luck, which is always a possibility, or that our assumptions regarding size distributions are flawed, or that the object is not what it appears to be. That final possibility is what consistently steers discussions toward technological hypotheses. If Oumuamua is artificial, a manufactured construct rather than a natural comet, then size statistics do not constrain it. An advanced civilization capable of interstellar travel would construct spacecraft of whatever dimensions served their purposes. They are not bound by the natural distribution of icy debris in the galaxy. A 46-kilometer spacecraft, while extravagant by human standards, lacks a comparative frame of reference for what alien engineering might deem conventional. Naturally, proposing that Oumuamua is artificial because it defies statistical expectations for natural objects constitutes circular reasoning of the most evident kind. We simply do not possess sufficient data to establish robust statistical expectations in the first place. 3 detections over an 8-year period yield a sample size of merely 3. Drawing definitive conclusions about population distributions from 3 data points is, at best, premature. However, this is precisely the source of frustration. We require more data. We need enhanced observations. We necessitate the kind of detailed imaging and spectroscopic analysis that multiple spacecraft were positioned to provide in early October. And we find ourselves in a state of waiting, dependent on institutions that operate with inherent slowness, burdened by layers of review and constrained by both budgetary and political considerations. In the interim, Oumuamua continues its cosmic journey. It has traversed Mars' orbital path. It is approaching perihelion. Soon, it will be obscured by the sun, rendering it invisible from Earth, engaging in whatever activities comets, spacecraft, or whatever it may be, undertake when unobserved. The question of its mass remains unresolved. The ambiguity surrounding its size persists, and the statistical arguments for or against a natural origin remain suspended in uncertainty, awaiting data that may or may not eventually materialize. Chapter 5. The Question of Origin. From whence did Oumuamua originate? Not in the immediate context of its trajectory through our solar system, that is well established, but rather in the profound sense of which star system originally birthed this object billions of years ago. Tracing the origins of interstellar objects presents immense challenges. These entities have traversed the galaxy for eons, subjected to gravitational perturbations from passing stars, interactions with molecular clouds, and the cumulative effects of galactic rotation. Minor inaccuracies in current velocity measurements amplify exponentially when extrapolated backward through millions or billions of years. A research team led by Matthew Hopkins at the University of Oxford tackled this challenge utilising the Oxford model, a sophisticated simulation that integrates data from the Gaia spacecraft stellar census with models of protoplanetary disk chemistry and galactic dynamics. They inputted Oumuamua's observed velocity and position, then simulated its trajectory backward in time, identifying stars that the comet might have passed in proximity during its journey. The paramount parameter is velocity. Upon entering our solar system, Oumuamua was receding from the galactic centre at a velocity of 51 kilometers per second relative to the Sun. It was also ascending through the galactic plane at a velocity of 18.5 kilometers per second. This vertical component, referred to as the W velocity in galactic coordinates, is unusually high. The majority of nearby stars and objects within the solar neighbourhood exhibit lower vertical velocities, typically under 10 kilometers per second. Stars and objects in the galactic disk orbit primarily within the plane, with some oscillatory motion above and below, but Oumuamua's vertical velocity surpasses this typical oscillation. This suggests that Oumuamua belongs to what astronomers term the thick disk population rather than the thin disk. The Milky Way's disk actually comprises two distinct components. The thin disk harbours younger stars, metal-rich stars with compositions akin to the Sun, orbiting in a relatively planar configuration. The thick disk, conversely, contains older stars, metal-poor stars formed during an earlier epoch when the galaxy was younger and less chemically enriched, orbiting in a more vertically extensive distribution. Objects originating from the thick disk typically possess higher vertical velocities due to their orbital planes being inclined relative to the primary galactic plane. If Oumuamua originated from the thick disk, it is likely ancient. Hopkins and his colleagues estimated its age to be between 7.6 and 14 billion years, with a 68% confidence interval. For reference, the Sun is 4.6 billion years old. Oumuamua could predate our entire solar system by billions of years. It might have formed when the universe was less than half its current age, rendering it a relic from an earlier phase of galactic history. An independent analysis conducted by Asta Taylor and Darrell Seligman arrived at similar conclusions, estimating Oumuamua's age to be between 3 and 11 billion years. The breadth of this range arises from the inherent assumptions required to translate galactic kinematics into age estimations, particularly concerning the formation and evolution of the thick disk. Nevertheless, both studies concur that Oumuamua represents an ancient object, one that has been traversing the galaxy for an exceptionally prolonged period. Its chemical composition further supports this interpretation. Thick disk stars exhibit lower metallicity compared to thin disk stars. In astronomical parlance, metallicity refers to the abundance of elements heavier than hydrogen and helium. The primordial universe consisted essentially of only hydrogen and helium. stellar fusion processes transmute these light elements into heavier ones, such as carbon, oxygen, nitrogen, silicon, and iron. Upon their demise, particularly through supernova explosions, stars disperse these heavier elements into the interstellar medium. Subsequent generations of stars and planets form from gas clouds enriched with these metals. Thick disk stars originated earlier, before substantial metal enrichment had occurred. Planets and comets forming within these systems would have compositions reflecting the lower metallic abundances of their birth environments. If Oumuamua formed within a low metallicity protoplanetary disk, its composition would differ from that of solar system comets. The elevated ratio of carbon dioxide to water could indicate formation beyond the carbon dioxide frost line in a disk exhibiting particular thermal and chemical gradients. All these factors collectively point toward Oumuamua originating from an ancient star system within the thick disk. But which specific star? A research team led by Yi-Yang Guo attempted to trace Oumuamua backward through the galaxy to pinpoint potential parent stars. They utilized Gaia data encompassing over 13 million stars, running simulations to ascertain which stars 3i Oumuamua might have passed in close proximity during the preceding 10 million years. In this context, close proximity denotes a distance of approximately 6.5 light-years. At such a distance, stellar gravity possesses the potential to sufficiently perturb an object's trajectory to either capture it into a bound orbit or eject it into interstellar space. The simulations identified 93 nominal encounters, representing stars that 3i Oumuamua purportedly passed relatively near during its reconstructed path. Of these, 62 were deemed significant at the 2 sigma confidence level, meaning their orbital uncertainties did not entirely preclude the possibility. However, herein lies the critical issue. None of those encounters resulted in meaningful perturbations. The star identified as the most potent potential perturber, catalogued as Gaia DR368635913895296164, passed within 0.3 parsecs of 3i Oumuamua with a relative velocity of 35 km per second. Such an interaction should have altered Oumuamua's velocity by approximately 510 thousandths of a kilometre per second. This is utterly negligible. To provide perspective, 3i Oumuamua currently travels at 60 km per second. A velocity change of half a metre per second is insignificant to the point of being irrelevant. The conclusion derived is that no stellar flyby within the past 10 million years and within 500 parsecs of the Sun can adequately account for Oumuamua's current trajectory. The comet was not recently ejected from any proximate star system. It has been travelling through interstellar space for a duration far exceeding 10 million years, potentially spanning hundreds of millions or even billions of years. This paints a fascinating, albeit sobering picture. Oumuamua is a wanderer in the most profound sense of the term. It originated around some unknown star billions of years ago. Gravitational interactions, likely with a giant planet or a close stellar encounter, ejected it from its birth system. Since then, it has been drifting through the galaxy, intermittently passing through star systems such as ours, but primarily traversing the vast empty expanses between stars. During this extended journey, its surface has been bombarded by cosmic rays. Interstellar dust grains have abraded it. Ultraviolet radiation from distant stars has chemically altered its surface. All these effects cumulatively modify the object's properties over time, altering its composition in ways that may obscure its original chemical signature. This is precisely why comparing Oumuamua to solar system comets yields only limited insights. Solar system comets are pristine, preserved in a state of cold stasis within the Oort cloud or Kuiper belt since the solar system's formation 4.6 billion years ago. Oumuamua, conversely, has been exposed to the interstellar environment for potentially 3 times that duration. The thick disk origin further raises pertinent questions regarding its formation conditions. Planetary systems frequently orbit stars within the dense galactic disk. Missions like Kepler, alongside various exoplanet surveys, have revealed planets around stars with limited metallic content. However, the structures of these planetary systems diverge from those found around metal-rich stars. Reduced metallicity implies a scarcity of solid material during planetary formation. Consequently, rocky planets may be smaller or less prevalent, and gas giants might develop through different processes. The arrangement of planets, including their orbital spacing and masses, exhibits a correlation with the metallicity of their parent star. If Oumuamua, for instance, originated in a low metallicity environment, it might represent the typical cometary material found in thick disk planetary systems, unlike the thin disk systems to which our own solar system belongs. Its distinctive composition, while appearing unusual to us, could be commonplace for its stellar population. Nevertheless, these notions remain hypothetical. We cannot definitively pinpoint its host star, nor can we fully reconstruct the detailed trajectory of Oumuamua's cosmic journey. While we can ascertain its present velocity and infer its galactic population membership, whether it hails from the thick or thin disk, its specific origins and the events it encountered along its path are obscured by the statistical background noise of galactic motion. Some researchers have investigated the possibility of a connection between Oumuamua and Borisov. The conjecture is that they might have been ejected from the same stellar system at different epochs, or perhaps even originated from the same parent comet that later fractured. However, their observed velocities do not support this hypothesis. Borisov and Oumuamua arrive from entirely disparate directions with distinct velocity vectors. Oumuamua's velocity further sets it apart. The velocities of these three objects do not indicate a common origin within recent galactic history. They are truly independent interstellar visitors, each carrying its own unique narrative. This very independence bolsters the argument that interstellar objects are a common phenomenon. If we have detected three completely unrelated visitors within an 8-year span, it suggests that the galaxy is replete with such wanderers. The vast expanse between stars is not empty. It is populated by innumerable celestial bodies, fragments from planetary systems scattered across the Milky Way, all traversing their individual paths and occasionally intersecting with star systems like ours. The majority of these objects are too diminutive for detection. We only observe those that happen to pass sufficiently close, are large enough, or are active enough to reflect adequate light for our telescopes. Our detection capabilities inherently bias our sample towards larger, brighter objects. The actual population includes a vastly greater number of smaller bodies that remain invisible to us. This leads to projections regarding future discoveries. The Vera C. Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is slated to commence full operations by late 2025. The Rubin Observatory will systematically scan the entire observable sky every few nights, cataloguing all celestial changes and movements. Its sensitivity and comprehensive coverage will facilitate the detection of many more interstellar objects, potentially numbering in the dozens annually once the survey reaches its peak capacity. These forthcoming detections will finally furnish the statistical data set necessary for a proper characterization of interstellar object populations. We will be able to determine their size distribution, velocity distribution, and compositional distribution. We will identify rare outliers and common types, and we will develop a classification system for interstellar visitors, akin to the taxonomies we have for asteroids and comets within our own solar system. In this context, Oumuamua serves as a pioneer. It is one of the initial arrivals preceding our development of systematic survey capabilities that would place it within a proper comparative framework. This renders it both exceptionally fascinating and deeply frustrating. It is fascinating because every detail assumes significance when our sample size is merely 3. It is frustrating because interpreting these details without comparative population data necessitates informed conjecture. However, the age of Oumuamua introduces a philosophical dimension to these considerations. If this object is 10 billion years old, It formed during an era when the universe presented a markedly different appearance. The Milky Way was younger and more dynamically active, with vigorous star formation occurring throughout its disk. Galaxies were engaging in more frequent collisions and mergers. The cosmic environment differed in fundamental ways. An object of such antiquity has borne witness to the galaxy's evolutionary history. It has been traversing space for a duration exceeding the existence of Earth itself. Our entire solar system, our planet, the entirety of life's history on Earth, everything we comprehend and cherish, all of it transpired while Oumuamua was already ancient, already a solitary wanderer among the stars. There is a profound sense of humility in this perspective, in encountering a messenger from the distant past, from a time and place we can never physically visit, but can dimly reconstruct through astronomical observation. If Oumuamua possessed the capacity to communicate, if we could somehow decipher the complete history embedded within its composition and structure, what revelations would it offer? What stars has it passed? What cosmic events has it witnessed? Has it ventured into other planetary systems prior to our own? Have other civilizations observed it, perhaps even studied it in the same manner we are currently attempting? These inquiries venture into the realm of speculation, yet they are not devoid of scientific merit. They serve as the impetus for the detailed study of interstellar objects. Every measurement, every spectral analysis, every captured image contributes a fragment to the reconstruction of this history. In a sense, we are like archaeologists, examining artifacts from remote eras and distant locations, endeavouring to decipher the narratives inscribed in chemistry and physics. Chapter 6. The Awaiting Observers. December 2nd, 2025. This is the date when the European Space Agency's JUICE spacecraft is scheduled to commence its observation campaign targeting Oumuamua. By this juncture, the comet will have completed its closest approach to the Sun, emerged from its proximity, and entered what is anticipated to be its most active phase. The solar heating experienced during its close path should instigate maximal outgassing. If Oumuamua is a naturally occurring comet, December will showcase its full splendour, a luminous coma, a conspicuous tail, and potentially even fragments resulting from thermal stress exceeding its structural integrity. JUICE, the Jupiter Icy Moons Explorer, was not originally designed for the observation of interstellar comets. Its mission objective is to investigate Jupiter's large moons, Europa, Ganymede, and Callisto, seeking evidence of subsurface oceans and assessing their potential habitability. The spacecraft's scientific payload comprises cameras, spectrometers, radar, magnetometers, and particle detectors, all optimized for the study of icy moon geology and potential habitable environments. However, in November 2025, JUICE finds itself strategically positioned to observe Oumuamua. The spacecraft will deploy multiple instruments. Janus, the Jovian acquirer of Moon's Observatory, a camera system with 13 filters covering wavelengths from 360 to 1080 nanometers, is capable of capturing color imagery and performing rudimentary compositional analysis based on spectral reflectance. MAGIS, the Moon and Jupiter Imaging Spectrometer, spans visible to infrared wavelengths, enabling compositional mapping with significantly finer spectral resolution than Janus. The UVS ultraviolet spectrograph analyzes emissions in the extreme and far ultraviolet spectrum, proving particularly useful for identifying specific molecules such as water, carbon monoxide, and hydrogen. Additionally, there is the PEP instrument, the Particle Environment Package. PEP is actually composed of 6 distinct sensors that measure electrons, ions, and neutral atoms across a broad energy spectrum. When a comet releases gases, these expelled molecules interact with the solar wind. Some become ionized by solar ultraviolet radiation, while others undergo charge exchange reactions. The outcome is a complex particle environment surrounding the comet, which PEP is equipped to characterize, thereby revealing details about its composition an outgassing rate that optical observations alone cannot ascertain. The advantage JUICE possesses over Earth-based observations at this specific time stems from its unique vantage point. As Oumuamua reappears from behind the Sun in early December, it will again be visible from Earth, but the viewing angle will be restricted. We will observe it from a single perspective. JUICE, positioned elsewhere within the solar system, will provide an observation from a different angle. The integration of these multiple perspectives, Earth-based and JUICE-based, will facilitate a stereoscopic reconstruction of the coma's three-dimensional structure. Consider attempting to comprehend the three-dimensional form of a cloud by observing it from directly beneath. You perceive a two-dimensional projection, merely a shape in the sky, without the ability to discern its depth or true dimensions. Introducing a second viewpoint from the side instantaneously clarifies the three-dimensional architecture. This is precisely the benefit of multi-angle observations. They transform flat projections into spatial maps. Furthermore, JUICE will observe Oumuamua shortly after its perihelion passage, capturing it during a phase that is potentially more active than what Earth-based telescopes might observe during the summer and early autumn months. If the perihelion passage triggers enhanced outgassing, if jets become more pronounced, or if the coma's colour or composition undergoes alterations due to thermal processing, JUICE will document these changes while they are still fresh. However, all of this comes with a previously mentioned caveat. The data will not be transmitted until February 2026, a delay of 3 months following the observations themselves. During these 3 months, the world will observe Oumuamua through ground-based telescopes, comparing its post-perihelion behaviour to its pre-perihelion behaviour, noting any shifts, anomalies, or deviations from predicted trajectories. The JUICE data will eventually provide supplementary context, but not in real time. Ground-based observations will resume once Oumuamua sufficiently separates from the Sun's proximity in the sky. Telescopes with an aperture class of 8 inches or larger should be capable of detecting the comet at its projected magnitude. Networks of amateur astronomers, alongside professional observatories, will track it nightly, measuring its brightness, monitoring for any outbursts, and verifying whether its trajectory aligns with orbital predictions. This is where citizen science plays a pivotal role. When institutional resources are constrained, when government agencies operate with deliberate speed, and when proprietary data release is postponed, amateur astronomers bridge the gap. They are unburdened by bureaucratic limitations. They possess their own equipment. They freely publish their findings online. The global network of amateur observers, interconnected through forums, social media, and collaborative platforms, functions as a distributed observatory, providing coverage across time zones and hemispheres. Simeon Schmaus, who previously processed images from the Perseverance rover's NavCam, exemplifies this community. He's not affiliated with NASA or the ESA, nor is he a professional planetary scientist. He's an astrophotographer skilled in image processing, adept at extracting faint signals from noisy data, and dedicated enough to spend hours refining his techniques. When NASA's data pipeline encountered delays during a government shutdown, individuals like Schmaus stepped in, downloading raw archives, stacking image frames, and disseminating their findings. This democratization of astronomy has experienced a dramatic acceleration over the past 2 decades. Sophisticated image processing software, once requiring high-end workstations, now operates on standard laptops. Telescope mounts with computerized tracking, which previously cost tens of thousands of dollars, can now be acquired for hundreds. Cameras sensitive enough to image faint celestial objects, a capability that once necessitated access to professional observatories, can now be attached to backyard telescopes. The barriers to entry have effectively dissolved. One can acquire an 8-inch Schmidt-Cassegrain telescope, a competent CCD camera, and a laptop equipped with processing software, thereby becoming equipped to contribute meaningful observations. While the resolution will not rival that of the Hubble Space Telescope or the sensitivity of professional observatory instruments, the data gathered will augment collective understanding, and when dozens or hundreds of amateur observers worldwide direct their equipment towards the same celestial target, the aggregated dataset becomes substantial. Oumuamua is highly likely to attract this level of attention. The ensuing controversy, the ongoing speculation, and the institutional silence collectively fuel public interest. When individuals become invested in an object and seek answers, they channel resources towards its investigation. Amateur networks will orchestrate observation campaigns. They will coordinate timing windows. They will process each other's data. They will compare their observations and discuss their findings. If Oumuamua exhibits any unexpected behavior, amateur observers will be among the first to detect it. Should its brightness suddenly surge in an outburst, someone will notice within hours. If its trajectory deviates from predictions, orbital analysis enthusiasts will flag the discrepancy. If multiple objects appear where only one was previously observed, indicating fragmentation, photographic evidence will document it. The global network provides a crucial layer of redundancy. There is no single point of failure. The object cannot be concealed through institutional secrecy when thousands of independent observers are scrutinizing it. However, observers will only be able to witness phenomena occurring after perihelion, the critical juncture, the passage behind the sun, the period of peak thermal stress, and the most logical time for any hypothetical maneuvering or probe deployment. This crucial moment will remain unobserved from Earth. Data from the JUICE mission will assist in reconstructing events, but with a 3-month delay. The immediate post-perihelion observations will reveal outcomes, not the underlying causes. This presents an interpretive challenge. Suppose Oumuamua emerges from perihelion on a trajectory that deviates slightly from predictions, not a dramatic shift, but a change of a few tenths of a percent. Such a degree of alteration could be attributed to outgassing jets, where escaping gas from the nucleus generates minute thrust forces. Over weeks and months these forces accumulate, resulting in measurable velocity changes, a phenomenon known as the rocket effect, which is well documented in comets. Given the existence of the rocket effect, how can one differentiate between natural outgassing that coincidentally nudges the comet off course and deliberate maneuvering that mimics natural outgassing? The answer is that it cannot be done conclusively. One can model the expected outgassing based on solar heating and an estimated nuclear size. One can measure actual outgassing by observing the coma's brightness and spectral emission lines. If the observed outgassing accounts for the trajectory change, natural causes are invoked. If the trajectory change exceeds what the observed outgassing should produce, an anomaly is indicated. However, these measurements are accompanied by uncertainties, and the models incorporate assumptions. Distinguishing signal from noise demands meticulous analysis. Alternatively, suppose Oumuamua fragments. Comets fragment relatively frequently. Thermal stress induces fractures, rotational forces generate centrifugal stress, and internal pressure from vaporizing ices exploits weak points, causing the structure to break apart. If Oumuamua reappears as multiple fragments, is this due to natural fragmentation or the deliberate separation of a mothership from daughter probes? Again, additional evidence is required for differentiation. Natural fragments follow ballistic trajectories dictated by the geometry of the breakup. They separate slowly, typically at velocities of meters per second or less. Deliberate probes, conversely, could exhibit higher separation velocities, maneuver independently after separation, and display non-gravitational accelerations that natural fragments would not manifest. However, detecting these signatures necessitates precise astrometry over extended periods. Each fragment's position must be tracked with high accuracy, night after night, week after week, to accumulate sufficient data for orbital model fitting and the identification of deviations. This brings us back to the question of institutional capabilities versus those of citizen science. Professional observatories can provide the astrometric precision essential for these analyses. The tracking cameras utilized for near-Earth asteroid surveys, such as the Atlas network itself, achieve positional accuracies of fractions of an arcsecond. Over weeks of observation, this precision enables orbital determination sufficiently accurate to predict positions months or years in advance, and to detect subtle non-gravitational forces. Amateur equipment generally cannot match this level of precision. An 8-inch telescope might achieve astrometric accuracy of 1 to 2 arcseconds under optimal conditions, but this is an order of magnitude less precise than professional instruments. For bright objects moving slowly across the sky, amateur astrometry is adequate. For faint objects moving rapidly, where high precision is required to detect minute deviations, professional resources become indispensable. This is where institutional silence becomes significant. If NASA and the ESA release data promptly, if professional observatories coordinate observation campaigns, and if the global astronomical community marshals its full resources, we will maximize the scientific return from this rare opportunity. Conversely, if data becomes bottlenecked, if observations are delayed, or if coordination falters, our learning will be less than it could have been. The Galileo project, led by Avi Loeb, represents an effort to bridge this gap. The project operates 3 observatories, one in Massachusetts, one in Pennsylvania, and one in Nevada. These facilities are equipped with instruments specifically designed to detect and characterize unidentified anomalous phenomena, UAPs. The observatories employ multi-camera systems covering visible and infrared wavelengths, along with environmental sensors to correlate detections with atmospheric conditions. While the Galileo project's primary focus is UAP within Earth's atmosphere, its observatories are also capable of tracking objects in space. Loeb has stated that the Massachusetts Observatory will monitor the sky during and after Oumuamua's perihelion passage, searching for any correlated increase in UAP activity. The hypothesis being tested is whether the arrival of an interstellar object might trigger secondary phenomena, either through unknown natural physical processes or through hypothetical probe deployments. This line of inquiry moves beyond conventional astronomy into more speculative territory. The scientific mainstream would argue that there is no inherent reason to anticipate a correlation between the passage of an interstellar comet and atmospheric anomalies. However, Loeb's approach is to collect data and observe empirically, rather than to preemptively assume the outcome. If no correlation exists, the data will demonstrate this. If a correlation is found, it will demand explanation. The broader significance is that Oumuamua has catalyzed a variety of observation strategies, professional, amateur and purpose-built projects like Galileo. The object has captured attention in a manner that transcends typical cometry observations. Part of this is attributable to its interstellar origin, part stems from its anomalous characteristics, and part results from the controversy and speculation surrounding it. All these factors combine to ensure that when Oumuamua emerges from behind the Sun, numerous eyes will be observing it. Chapter 7: The Scientific Battlefield. Jason Wright maintains a blog titled astroph.com, where he chronicles his astrophysics research and occasionally offers critiques of the work of his peers. In July 2025, he published a detailed analysis of Avi Loeb's claims concerning Oumuamua. The post's title, Avi and Oumuamua, directly signals the confrontational nature of its content. Wright does not hold back, unequivocally dismissing Loeb's extraterrestrial spacecraft hypothesis as nonsense, and systematically refuting each claimed anomaly. Wright holds the esteemed position of Professor of Astronomy and Astrophysics at Penn State University, directs the Penn State Center for Extraterrestrial Intelligence, and serves on multiple scientific advisory boards. His credentials in the search for technosignatures, evidence of technological civilizations, are on par with, if not exceed, those of Loeb. When Wright criticizes Loeb's work, it is not from the perspective of a skeptic dismissive of all unconventional possibilities. Rather, it originates from a colleague within the same field who disagrees with the methodology and conclusions. The central focus of Wright's critique revolves around Loeb's handling of evidence. Wright meticulously traces Loeb's evolving statements about Oumuamua chronologically. On July 2nd, Loeb's initial blog post expressed enthusiasm for the discovery, but made no mention of alien spacecraft. On July 3rd, he was featured in an interview with the Daily Mail, where the possibility of extraterrestrial technology being involved was brought up. By July 4th, Loeb was asserting that the celestial body had to be significantly smaller than initial estimations or statistically improbable. By July 7th, he was discussing potential intercept mission scenarios. By the middle of July, he had fully embraced the hypothesis that Object 3-eyed Atlas could be artificial in origin. Wright contends that this progression indicates a predetermined line of reasoning. Instead of letting the data guide his conclusions, Loeb purportedly selected a conclusion early on, and then selectively emphasized evidence that supported it, while downplaying or dismissing any evidence that contradicted it. For instance, multiple observatories detected cometary activity around 3-eyed Atlas, characterized by the presence of gas and dust that created a visible coma. Loeb initially acknowledged this, but subsequently shifted his argument, claiming the observations were inconclusive and that the fuzzy appearance around the object could be a result of instrumental effects or motion blur rather than actual outgassing. The Very Large Telescope released images that clearly depicted a symmetrical coma surrounding 3-eyed Atlas, precisely what one would expect from a comet. Loeb dismissed these images as inconclusive, citing the object's motion and the inevitable smearing. However, Reich points out that the VLT team specifically compensated for motion in their image processing. The images were not blurred artifacts, they showcased genuine cometary activity. Wright also tackles the size argument. Loeb placed considerable emphasis on the estimated size of 10 to 20 kilometers, derived from early brightness measurements, arguing that this was too large to be consistent with interstellar comet populations. But as Wright observes, those were highly preliminary estimates based on assumptions about albedo that might not have been accurate. Subsequent observations suggested smaller dimensions. Loeb then pivoted to the Spherex infrared measurements, which indicated a size of 46 kilometers, using this as evidence that the object was anomalous. Yet, Wright questions whether the infrared data truly signifies nuclear size, or merely an extended dust cloud. Throughout his critique, Wright underscores that every feature of 3-eyed Atlas that was considered anomalous possesses plausible natural explanations. The absence of a prominent tail could be attributed to the viewing geometry, or the object being observed before significant outgassing commenced. The unusual chemical composition, rich in carbon dioxide and water vapor, is rare but not unprecedented. The trajectory alignment with the ecliptic plane, while unlikely, is not impossible. Statistics measure probabilities, not impossibilities. Unlikely events do occur. That is precisely what unlikely means. It does not imply prohibition. Wright's frustration becomes apparent when he discusses the impact of Loeb's actions on the broader field of technosignature research. Wright and other researchers involved in the search for extraterrestrial intelligence must uphold scientific credibility. They require funding agencies to seriously consider their proposals, journals to publish their findings, and colleagues to collaborate. When highly visible researchers make bold claims based on scant evidence, it affects the reputation of the entire field. Critics can seize upon such overreach and argue that technosignature research is inherently unserious, always leaning towards the most exotic explanation without adequate scientific rigor. This creates tension within the CT community. On one hand, the field requires visibility. Public interest fuels funding, and media coverage attracts students. Provocative claims about potential alien artifacts generate attention in ways that dry technical papers do not. On the other hand, the field necessitates respectability. It must be perceived as legitimate science, not as fringe speculation. Balancing these competing demands engenders ongoing debates regarding methodology, standards of evidence, and public communication. Loeb's response to his critics has been consistent. He portrays himself as a Galileo figure, a maverick challenging the established order. He argues that mainstream science is excessively conservative, too quick to dismiss unconventional ideas, and too invested in preserving existing paradigms. He highlights historical instances where scientists proposing radical new ideas faced resistance before eventually being vindicated. The underlying message is that his critics are the modern counterparts of those who rejected Galileo, defending outdated models against uncomfortable truths. This narrative possesses rhetorical power. Everyone appreciates an underdog story. The image of a solitary scientist bravely pursuing truth against institutional opposition resonates deeply. However, Wright and others argue that this portrayal is misleading. Lowe is not being persecuted. His papers are published, he holds a prestigious position at Harvard, leads well-funded research projects, and appears regularly in the media. If anything, he receives more attention than most scientists. The pushback he encounters stems not from an orthodoxy attempting to suppress him, but from colleagues identifying methodological issues with his work. The scientific process inherently includes criticism. When a hypothesis is proposed, others examine it, test it, and look for flaws. This is how science advances. The fact that colleagues criticize Lowe's claims about Three-Eyed Atlas does not imply they are closed-minded. It signifies they are fulfilling their role in evaluating evidence and offering alternative interpretations. Some criticism is severe, some is dismissive, but much of it is substantive, pointing to specific problems with data analysis or logical reasoning. Chris Lintott, a professor of astrophysics at Oxford, described Lowe's hypothesis of Three-Eyed Atlas being an alien probe as absolute nonsense. He emphasized that all available evidence indicates Three-Eyed Atlas is a comet with typical cometary properties once observational limitations and processing uncertainties are taken into account. Other astronomers echoed this assessment, some publicly and some privately. The prevailing consensus within the planetary science community is that Three-Eyed Atlas is a natural phenomenon. However, consensus does not equate to certainty. Science operates on provisional conclusions subject to revision when new evidence emerges. It is entirely possible that the majority view is incorrect. History is replete with examples where scientific consensus was later proven mistaken. Continental drift was dismissed for decades before plate tectonics gained acceptance. Prions, infectious proteins lacking nucleic acids, were considered impossible until Stanley Prusiner demonstrated their existence. The existence of exoplanets was doubted until the first confirmations in the 1990s. Therefore, the question arises, what would constitute sufficient evidence to overturn the consensus that Three-Eyed Atlas is natural? What observations or measurements would convince the skeptical majority that technological explanations warrant serious consideration? Lowe has proposed several criteria. If Three-Eyed Atlas maneuvers in ways inconsistent with natural outgassing, that would be significant. If it releases objects that then exhibit independent maneuvering, that would be nearly definitive. If it emits radio signals or other electromagnetic emissions inconsistent with thermal radiation, that would be compelling. If detailed imaging reveals geometric structures, regular patterns, or other hallmarks of artificial design, that would demand a re-evaluation. None of these signatures have been detected. Three-Eyed Atlas has not deviated from predicted trajectories beyond what might be caused by natural outgassing. It has not emitted anomalous signals. No images show artificial structures. The object behaves like a comet in almost every measurable way. The only unusual features are its chemical composition, which is rare but naturally explicable, and its trajectory statistics, which are unlikely but not impossible. Given this situation, most astronomers argue that Occam's razor favours the natural interpretation. When two competing hypotheses can both explain the observations, the simpler one should be preferred. A comet with unusual but natural properties is simpler than an alien spacecraft designed to mimic a comet. The technological hypothesis necessitates assuming that advanced civilizations exist, possess interstellar travel capabilities, chose to visit our solar system, constructed their spacecraft to resemble comets, and timed their visit to coincide with our technological capacity to detect interstellar objects. This is a substantial accumulation of assumptions. The natural hypothesis only requires that interstellar comets exist, which we have confirmed through 3 detections, and that some of these comets exhibit unusual properties, which would be expected given the diversity of planetary system formation conditions across the galaxy. This involves far fewer assumptions, making it the preferred explanation in the absence of compelling evidence to the contrary. However, Lowe might counter that this reasoning presumes knowledge of the probability distribution for these various assumptions. How confident are we that alien civilizations are rare? How certain are we that interstellar travel is difficult? Do we truly comprehend the range of motivations an alien civilization might possess? The Copernican principle, the idea that we are not special or unique, suggests that other civilizations likely exist elsewhere. The Fermi paradox, the apparent absence of evidence for these civilizations despite the high probability of their existence, demands explanation. One possible resolution to the paradox is that alien civilizations communicate or travel in ways we have not yet recognized. Interstellar objects could represent one such mode. This philosophical debate regarding prior beliefs, concerning the assumptions we bring to the evaluation of evidence, underpins much of the controversy. Different scientists with different priors arrive at different conclusions from the same data. Those with a very low prior for alien technology require overwhelming evidence to alter their beliefs. Those with higher priors, like Lowe, update their beliefs more readily based on ambiguous evidence. There is no purely objective way to resolve this. Bayesian reasoning, the mathematical framework for updating beliefs based on evidence, necessitates the specification of prior probabilities. Where do these priors originate? Partly from previous experience and data, but ultimately from judgment calls about how to weigh different possibilities. Scientists disagree on these judgment calls, leading to disagreements in interpretation, even when they concur on the raw observations. What is frustrating for all parties involved is the absence of definitive data. If the Mars flyby images had been released immediately, and if they had shown clear, detailed structures, much of the debate would have been settled. If ground-based observations during perihelion had been possible, allowing us to observe Three-Eyed Atlas continuously through its most active phase, we would have better constraints. Instead, we have incomplete data, delayed releases, observational gaps, and ample room for competing interpretations to persist. The scientific battleground over Three-Eyed Atlas illustrates the nature of astronomy when dealing with rare, poorly observed phenomena. It is not neat, it is not decisive. It is a complex process involving competing hypotheses, insufficient evidence, professional disagreements, and public speculation. Eventually, either Three-Eyed Atlas will exhibit something unambiguous that compels consensus, or it will depart the solar system with its nature still a subject of debate, adding another mystery to the extensive list of unresolved questions about our universe. Chapter 8. The Social Media Storm. While scientists engaged in debates about methodology and evidence standards in journals and blogs, a parallel discourse erupted across social media platforms. Three-Eyed Atlas became a trending topic on X, formerly Twitter, with thousands of posts analyzing images, sharing speculation, and disseminating misinformation. Reddit communities dedicated entire threads to tracking every development. YouTube creators published videos with titles promising sensational revelations. TikTok users produced short clips explaining the comet or warning of potential dangers. This pattern follows a familiar trajectory for astronomical phenomena that capture public imagination. Initial excitement spreads through early adopter communities, astronomers, space enthusiasts, and science communicators. Subsequently, mainstream attention is piqued as news outlets cover the story. From there, the narrative fragments into countless variations as different voices contribute their interpretations, corrections, embellishments, and fabrications. Some social media discussions remained grounded in actual observations and scientific analysis. Amateur astronomers shared their telescope images, exchanged notes on visibility windows, and discussed processing techniques. Science communicators endeavoured to provide accurate context, explaining what Three-Eyed Atlas is, its origin, and why it is of interest. These posts frequently included disclaimers about uncertainty, acknowledgements of unknown factors, and references to expert opinions. However, other content veered into speculation unconstrained by evidence. Some posts definitively claimed Three-Eyed Atlas was an alien mothership, citing Avi's papers while omitting his caveats. Others warned it posed an imminent threat to Earth, despite its trajectory remaining far beyond Mars' orbit. Conspiracy theories proliferated. Some suggested governments were concealing the truth about Three-Eyed Atlas. Others linked it to unrelated events, political developments, economic forecasts, and religious prophecies. One particularly viral post falsely attributed statements to physicist Michio Kaku, claiming he had stated Three-Eyed Atlas was accelerating towards Earth with potential hostile intent. The post included a manipulated screenshot from a television interview, showing Kaku on screen with overlaid text suggesting he had made these dramatic claims. The image spread rapidly, accumulating hundreds of thousands of views before fact-checkers identified it as fabricated. The actual interview screenshot originated from February 2025, months before Three-Eyed Atlas was even discovered. Someone had taken an unrelated appearance by Kaku, added misleading text, and presented it as current news. This type of manipulation occurs frequently with scientific topics. Public figures are misquoted or have their statements taken out of context to support narratives they never endorsed. The fact-checking initiative PolitiFact, an operation by factcheck.org, investigated the Kaku claims and published a detailed debunking. They traced the image to its source, confirmed the date of the original interview, and found no record of Kaku making any statements about Three-Eyed Atlas. But by the time fact-checks emerged, the false claims had already propagated through networks of users eager to believe the sensational narrative. This exemplifies a fundamental challenge in contemporary information environments. Truth and falsehood disseminate at different rates through different channels. Accurate but mundane information, such as Three-Eyed Atlas is an interstellar comet following a predictable trajectory that poses no threat to Earth, garners modest engagement. Sensational but false information, such as scientists confirm alien spacecraft approaching Earth with hostile intent, generates massive engagement because it triggers emotional responses, fear, excitement, and curiosity. Platform algorithms are optimized for engagement. Posts that generate clicks, shares, comments, and time spent on the platform are amplified. Posts that users scroll past without interaction are buried. This creates a selective pressure, favoring content that provokes strong reactions regardless of its accuracy. Content creators, whether motivated by genuine belief, a desire for attention, or financial incentives from advertising revenue, learn to craft messages that maximize engagement. The consequence is an information ecosystem where facts compete with fiction on unequal terms. Scientists carefully hedging their statements with appropriate qualifiers of uncertainty are drowned out by confident voices making definitive claims. Nuanced analysis requiring thought and attention loses out to simple narratives demanding only an emotional reaction. The meticulous process of science, hypothesis, evidence, revision, consensus building appears dull and slow compared to the rapid-fire provocations of social media discourse. Three-Eyed Atlas became a canvas onto which people projected their existing beliefs. Those already convinced that governments conceal evidence of extraterrestrial contact saw NASA's silence as confirmation. Those skeptical of institutional authority interpreted the delayed image releases as intentional concealment. Those interested in apocalyptic scenarios transformed the comet into a threat, despite its trajectory keeping it millions of kilometers from Earth. One persistent narrative claimed military forces were preparing to deflect or destroy Three-Eyed Atlas. Posts referenced alleged mobilizations, secret Pentagon meetings, and coordination between international defense agencies. These claims lacked any factual basis. No such mobilizations occurred. No credible sources reported military interest in Three-Eyed Atlas beyond standard space situational awareness that monitors all significant solar system objects. However, the narrative persisted because it aligned with a particular worldview. If Three-Eyed Atlas were a threat, then naturally military forces would respond. If governments conceal information, then naturally they would not announce their plans. The absence of evidence becomes evidence of concealment. Every denial reinforces the conspiracy theory because naturally, conspirators would deny the conspiracy. This logical structure renders such theories unfalsifiable, immune to correction through ordinary means. Other social media users approach the situation differently, treating Three-Eyed Atlas as entertainment rather than a genuine mystery. Memes proliferated. One popular format featured the Doomsday Machine from Star Trek, with captions humorously commenting on humanity's reaction to interstellar visitors. Another format utilized the Disaster Girl meme template, with images of Three-Eyed Atlas photoshopped into the background. These humorous takes acknowledge the speculation while maintaining an ironic detachment. This entertainment framing serves a social function. It allows individuals to engage with the topic without committing to specific beliefs. One can share a joke about Three-Eyed Atlas being an alien spacecraft without actually believing that claim. The humour fosters a sense of common ground, a way to participate in the cultural moments surrounding the discovery without becoming entangled in contentious debates about reality. However, humour and misinformation exist on a continuum. What begins as obvious satire can be taken literally by audiences who fail to recognise the joke. Screenshots of satirical posts are shared without context. Parody accounts are mistaken for legitimate sources. The boundaries blur between entertainment, speculation, misinformation, and deliberate deception. Content moderation teams on social media platforms face challenging decisions. How should posts making false claims about scientific topics be handled? If someone states that Three-Eyed Atlas is an alien spacecraft approaching Earth, is that dangerous misinformation requiring removal, or is it protected speculation and opinion? Different platforms apply varying standards. Some adopt a laissez-faire approach, permitting most content unless it directly incites violence or harassment. Others attempt to attach warning labels or fact-check notices to dubious claims. Neither approach fully resolves the issue. Heavy moderation risks censoring legitimate debates and fueling accusations of platform bias. Light moderation allows misinformation to spread unchecked. The sheer volume of content, millions of posts daily across multiple platforms, makes consistent enforcement nearly impossible. Automated systems flag potential violations, but they make errors, removing innocent content while overlooking actual problems. For researchers studying Three-Eyed Atlas, this social media storm presents additional complications. When attempting to communicate scientific findings to the public, they must contend with a deluge of other voices, some helpful, many not. Journalists contact scientists for quotes. The quotes could end up in published articles juxtaposed with unverified conjecture from ordinary social media participants, presented as equally valid. The proportion of meaningful information to irrelevant noise becomes unmanageable. Certain scientists engage directly on social platforms, aiming to disseminate accurate facts and counter misinformation. Aviv maintains a consistent presence on X, sharing links to his blog posts and addressing inquiries. Other celestial researchers utilize Twitter threads to elucidate the principles of orbital motion or interpret novel astronomical findings. These endeavors reach individuals who might not otherwise consult scientific journals or browse astronomy-focused websites, thus injecting expert knowledge into arenas where unfounded claims often hold sway. However, participating in social media necessitates considerable time and personal resources. Scientists are already occupied with their primary responsibilities: teaching, conducting research, authoring papers, and attending conferences. dedicating hours to Twitter, responding to questions and refuting false narratives detracts from these fundamental duties. Not every scientist possesses the natural aptitude or the inclination for public discourse. Some prefer their work to be disseminated through formal channels rather than engaging in online disputes. This disparity creates an imbalance. Those most inclined to promote sensationalistic assertions frequently have more available time for social media than active researchers. A scientist might publish an accurate explanation once and then return to other tasks. Meanwhile, numerous accounts persist in propagating false narratives, engaging with comments, sharing humorous images, and keeping their version of events in circulation. The sheer volume eclipses the quality. Furthermore, there's the issue of how to communicate when scientific consensus itself is not definitive. In the case of 3 Atlas, experts genuinely hold differing views on certain interpretations. Lowe suggests that the anomalies warrant consideration of technological hypotheses. Wright believes that natural explanations are sufficient. How does one convey such disagreements to the general public without fostering the impression that scientists are entirely uninformed, or that all possibilities are equally uncertain? The scientific method inherently incorporates uncertainty as a characteristic, not a flaw. Theories remain provisional, subject to modification with the advent of new evidence. Levels of certainty fluctuate based on the amount of supporting data for a conclusion. This nuanced approach to knowledge acquisition does not translate readily into the realm of social media discourse, where individuals expect unambiguous answers. When a scientist states, "We're not certain yet," audiences sometimes interpret this as scientists are clueless. Instead of recognizing that uncertainty represents an honest appraisal of current knowledge, NASA's endeavor to address public apprehension regarding 3 Atlas highlights these communication hurdles, particularly as viral posts propagate false claims about the comet's trajectory and its supposed threat to Earth. The agency attempted to offer reassurance. Their official pronouncement stressed that 3 Atlas posed no peril, that its closest proximity to Earth was millions of kilometers distant, and that its flight path was well understood and predictable. However, for those already skeptical of NASA's pronouncements, these assurances had minimal impact. If one suspects that government agencies deliberately mislead regarding extraterrestrial matters, then official denials lose all credibility. Indeed, they might amplify suspicions. This dynamic places institutions in an untenable situation. Remaining silent fuels conspiracy theories about hidden information. Issuing denials, conversely, fuels conspiracy theories about cover-ups. No communication strategy can fully allay the concerns of audiences operating under different frameworks of understanding. This broader phenomenon extends beyond 3 Atlas to the field of science communication as a whole. Whenever a subject captures public fascination, be it climate change, vaccines, artificial intelligence, or space exploration, the same patterns emerge. Experts strive to present accurate information, acknowledging inherent uncertainties. Activists and advocates promote specific viewpoints aligned with their personal values. Opportunists leverage public attention for personal advantage. Conspiracy theorists integrate the subject into their existing belief systems. Comedians and creators of digital content utilize it for amusement. All these voices contend for attention within a shared informational landscape, where the distinctions between expertise and mere opinion become blurred. Perhaps a resolution lies in reassessing how scientific organizations engage with the public. Current methods, such as press releases, infrequent interviews, and official statements, were devised for an era when media gatekeepers regulated the flow of information. Journalists scrutinized sources, provided context, and distinguished meaningful content from trivialities. While that system had its own inherent issues and biases, it did establish a degree of filtration. Social media has bypassed these gatekeepers, enabling anyone to publish directly to a global audience. This democratization offers advantages, including the amplification of diverse perspectives, swift information dissemination, and grassroots mobilization. However, it also presents challenges such as the proliferation of misinformation, susceptibility to manipulation, and the algorithmic amplification of extreme content. Adapting scientific communication to this environment remains an ongoing experimental process with uncertain results. Chapter 9. The Emergence in December. The early part of December 2025 will signify a crucial juncture. 3 Atlas, having been concealed behind the Sun for several weeks, will reappear in positions observable by ground-based telescopes. The celestial alignment will initially place it low in the pre-dawn sky, visible for only a couple of hours before sunrise. Venus will be in close proximity, a bright and easily discernible celestial body, serving as a reference point for locating the significantly fainter comet. The projected apparent magnitude of around magnitude 10 positions, 3 Atlas at the threshold of what binoculars can detect under conditions of minimal light pollution. An experienced observer with high-quality equipment might discern it as a diffuse patch, distinct from the surrounding stars, but for unequivocal confirmation, a telescope is necessary. An aperture of 8 inches provides a comfortable margin. Larger instruments will reveal more intricate details, potentially showcasing the structure of the coma, and perhaps even a faint tail if one has begun to form. What observers witness during those initial nights of its reappearance will provide answers to immediate questions. Is 3 Atlas still intact? Does it appear as a single entity or multiple fragments? Has its brightness changed drastically from pre-perihelion observations? Is there evidence of tail development? Does its trajectory align with predictions or indicate deviations? These observations will originate from dozens of locations concurrently. Amateur astronomy clubs coordinate their observation efforts through online forums and mailing lists. An observer in Australia might be the first to witness 3 Atlas ascending above their eastern horizon. They will then post initial reports, estimates of its brightness, and descriptions of their observations. Hours later, observers in the Middle East will take up the watch, followed by Europe and then the Americas. This sequential relay will construct a continuous observational record spanning days and weeks. Professional observatories will also contribute to this endeavour. Survey telescopes, typically tasked with tracking asteroids, will be directed towards 3 Atlas to precisely measure its positions for astrometric analysis. Spectroscopic instruments will analyse the chemical composition of the coma, investigating whether the perihelion passage altered the composition of its outgassing products. Photometric monitors will track variations in brightness that could signify rotational activity or outburst events. The collected data will be integrated into databases managed by the Minor Planet Center, which serves as the International Astronomical Union's central repository for observations of comets, asteroids, and other minor bodies within our solar system. Astronomers globally will access this information, refining orbital models, comparing observations from disparate instruments and locations, and searching for patterns or anomalies. If 3 Atlas fractured during its perihelion passage, the initial observations will reveal multiple objects where only one was previously observed. Each fragment will follow its own slightly altered trajectory, dependent on the velocity and direction of separation at the moment of breakup. Tracking these fragments over subsequent nights will allow for a reconstruction of when and how the fragmentation occurred. Natural fragmentation typically results in pieces that drift apart slowly, with relative velocities measured in meters per second. The fragments remain in relative proximity for weeks before gradually diverging into distinct orbits. However, let us consider a scenario where the observations indicate something different. Suppose multiple objects appear, but their separation velocities exceed what would be expected from natural fragmentation. Or suppose the objects exhibit non-gravitational accelerations, changes in velocity not attributable to outgassing from their surfaces, which would necessitate further explanation. In such a case, one would need to consider whether an event other than simple fragmentation took place. This hypothetical scenario remains speculative, as there is currently no evidence to suggest that 3 Atlas will fragment. Numerous comets successfully navigate their perihelion passages without breaking apart, particularly when their closest approach to the Sun occurs at a distance exceeding approximately half an astronomical unit. 3 Atlas, situated at 1.36 astronomical units, remains comfortably outside this critical zone. While it will experience significant thermal stress, it is unlikely to be catastrophic. The object should emerge intact unless its internal structure is exceptionally fragile or unless influences beyond natural cometary behaviour are at play. The question of trajectory becomes paramount during the December observations. Orbital predictions derived from pre-perihelion data assume that only gravitational forces are acting upon 3 Atlas. The Sun's gravitational pull is the dominant factor. Jupiter's gravity contributes smaller perturbations, and the other planets exert minuscule influences. When these forces are combined and the equations of motion are integrated forward in time, they yield predicted positions for any future date. However, comets are subject to non-gravitational forces resulting from outgassing. When jets of gas are expelled from the nucleus, they generate thrust, causing a slight alteration in the comet's velocity. These subtle changes accumulate over time. For comets exhibiting vigorous outgassing, these non-gravitational forces can modify the trajectory sufficiently to produce noticeable positional discrepancies after weeks or months if they are not accounted for in the models. Astronomers address this by incorporating non-gravitational acceleration terms into their orbital models. These terms include parameters that are adjusted based on observational data, treating the outgassing thrust as unknown variables to be determined alongside the orbital elements. If the fitted parameters are consistent with observed outgassing patterns, meaning the magnitude of the thrust aligns with the measured gas production rates, then it can be concluded that natural processes are responsible for the trajectory. Conversely, if the trajectory deviations surpass what would be anticipated from observed outgassing, a problem arises. Either the outgassing measurements are incomplete, failing to account for a component of the activity, or another force is acting upon the object. This is where meticulous observation becomes indispensable. Comprehensive spectroscopy is required to measure all emitted gas species. Photometry is needed to track brightness as an indicator of activity levels. Precise astrometry is essential for accurately measuring positions. The correlation of all these measurements allows for the differentiation between the effects of natural outgassing and potential external influences. The observations in December will serve as the initial test to determine whether the post-perihelion trajectory of 3 Atlas aligns with predictions. The data will accumulate on a night-by-night basis. After a week of observations, preliminary orbital fits will narrow the range of uncertainties. After 2 weeks, the constraints will tighten further. By the end of December, astronomers will possess a reliable understanding of 3 Atlas's future path and whether it deviates from expectations. Should deviations emerge, the scientific community will engage in debate regarding their significance. Minor deviations, falling within the range explainable by outgassing, will lead to research papers analysing the non-gravitational forces but are unlikely to provoke significant controversy. Substantial deviations, changes that appear inconsistent with natural cometary behaviour, will trigger intense scrutiny. Researchers will investigate potential instrumental errors, systematic biases in the observations, and alternative explanations. Only after exhausting conventional possibilities would attention shift to unconventional hypotheses. Concurrently, the JUICE spacecraft will be conducting its own observations between November the 2nd and November the 25th. These observations coincide with a period when 3 Atlas remains obscured behind the Sun from Earth's perspective. JUICE will observe the comet during and immediately after its perihelion, gathering data on its most active phase, but this data will not be transmitted to Earth until February 2026. This creates a peculiar informational void. Observers in December will witness the aftermath without precise knowledge of what transpired. They will see 3 Atlas in whatever state it is in post-perihelion, but they will lack the detailed observational record of the perihelion passage itself. The data from JUICE, upon its eventual arrival in February, will retroactively fill this gap, but for the intervening months, interpretation will rely on inference rather than direct observation. Suppose the December observations reveal 3 Atlas to be intact and on a trajectory consistent with natural outgassing, thereby supporting the conventional cometary hypothesis. The unusual pre-perihelion chemistry and other anomalies would remain points of interest but explicable within natural frameworks. The narrative would likely recede from public consciousness as the object becomes merely another interstellar visitor, unusual but not revolutionary. Alternatively, suppose the December observations uncover something unexpected. Multiple objects where only one was anticipated, but with separation characteristics inconsistent with natural fragmentation or trajectory deviations that exceed plausible outgassing effects, or spectroscopic signatures that do not match the composition of any known comets. Any of these discoveries would reignite the debate and necessitate further investigation. The inherent challenge with any anomalous observation lies in distinguishing genuine anomalies from artifacts. Instrumental errors do occur. Atmospheric conditions can distort measurements. Mistakes in data processing are not uncommon. Before asserting that something is truly anomalous, it is imperative to rule out mundane explanations. This requires cross-referencing observations from multiple independent sources, utilizing different instruments and conducted by different observers. If all observers witness the same phenomenon despite employing different equipment and methodologies, confidence in the observation's authenticity increases. Amateur and professional observers during December will effectively perform this cross-validation. If one telescope reveals something unusual, but others do not, suspicion naturally falls on an instrumental issue with that particular telescope. However, if multiple telescopes situated in different locations all detect the same feature, it instills greater confidence in its reality. The distributed network of observers provides a layer of redundancy and error, checking that is absent in observations made by a single facility. Social media will amplify whatever is observed. Every image, every measurement, every interpretation will be shared and discussed. This duality presents both advantages and disadvantages. The advantage lies in the rapid dissemination of information. Noteworthy findings spread swiftly, attracting attention and prompting additional observations. The drawback is that premature or erroneous reports also propagate rapidly, potentially causing confusion before corrections can catch up. Scientists typically prefer to verify their findings before making them public. The traditional process involves data collection, careful analysis, report writing, submission for peer review, and only then publication. This deliberate pace ensures accuracy, but sacrifices speed. Social media inverts these priorities, favoring expediency over thoroughness. Observations are posted within hours of collection, often with minimal analysis, and sometimes with speculative conclusions that extend beyond the support offered by the data. This inherent tension between scientific caution and public impatience manifests with every high-profile astronomical event. 3 Atlas will be no exception. The initial images depicting it post-perihelion will circulate immediately. Viewers will zoom in, adjust contrast, and search for features. They will compare these images with pre-perihelion photographs, looking for changes. They will assert their interpretations of what they see, some of which will be accurate, while others will not. Professional astronomers will proceed with their established protocols, irrespective of the social media noise. They will gather observations, process the data, apply calibrations, fit models, and eventually publish their findings through journals and databases. This scientific record will provide the definitive account of 3 Atlas's behavior, but it will emerge weeks or months after the initial social media surge. Ultimately, what matters is whether 3 Atlas's December reappearance necessitates any revisions to our understanding. If it behaves as a typical comet, adhering to predictable physics, exhibiting natural outgassing signatures, and maintaining trajectories consistent with gravitational and non-gravitational forces, then it validates our understanding of these objects as reasonably well established. Unusual chemistry and improbable trajectories would make it an interesting case study, but not a paradigm-shifting discovery. Conversely, if it exhibits behavior that cannot be naturally explained, something that compels the invocation of processes or technologies beyond current cometry models, then December 2025 will become a historically significant month. The first confirmed observation of something demonstrably artificial within our solar system would fundamentally alter astronomy, astrobiology, and humanity's perception of its place in the cosmos. The stakes, in essence, are considerable. Not in terms of immediate practical implications. 3 Atlas poses no threat regardless of its nature, but in terms of the knowledge gained about the universe and the potential existence of entities beyond Earth, the December observations could prove enormously significant, or they might simply add another data point to our catalogue of interstellar visitors, interesting but not revolutionary. We will not know until the observations are made. Until then, speculation will persist, shaped by incomplete data, competing interpretations, and the hopes or fears that individuals project onto this enigmatic visitor from the depths of space. Chapter 10. The Pattern and the Silence. Let us move beyond the technical specifics, the spectroscopy, orbital mechanics, and observation campaigns, to consider the broader pattern that 3 Atlas exemplifies. This is not the first instance of an astronomical discovery igniting speculation about non-natural origins, nor will it be the last. Understanding the reasons behind this phenomenon requires an examination of how we process unusual observations and the implications when institutions control access to information that the public urgently desires. Oumuamua established the precedent. When astronomers detected the first confirmed interstellar object in October 2017, its peculiar characteristics immediately sparked debate. Its elongated shape, its non-gravitational acceleration as it departed the solar system, and its apparent lack of visible outgassing despite that acceleration all seemed anomalous. Avi proposed that it might be a solar sail, a thin, reflective structure propelled by solar radiation pressure. The majority of astronomers favoured natural explanations, positing it was likely a comet with atypical outgassing properties or a fragment from a disrupted celestial body. This controversy unfolded across scientific journals, popular media, and social media platforms. Some scientists expressed their frustration with the extraterrestrial hypothesis, deeming it premature and unsubstantiated. Others defended the value of considering all possibilities, even improbable ones, when confronting unprecedented observations. The debate highlighted philosophical divergences concerning how science ought to approach ambiguous evidence supporting extraordinary claims. Borisov, discovered in August 2019, offered a contrast. It presented as and behaved like a comet from the moment of its detection. A distinct coma, an evident tail, spectroscopic signatures consistent with known cometary compositions, and trajectory changes attributable to outgassing. No one proposed alien origins for Borisov because nothing about it necessitated an exotic explanation. It represented what astronomers anticipated interstellar comets would resemble, based on our understanding of solar system formation and material ejection processes. 3 Atlas occupies a middle ground between these two extremes. It displays cometary activity, unlike Oumuamua. However, it also exhibits peculiar characteristics. Its chemical makeup, the statistical analysis of its flight path, and the ambiguity surrounding its dimensions set it apart from conventional celestial bodies like Boris. The central inquiry remains whether these unusual traits necessitate extraordinary explanations or simply represent natural variations within the broader spectrum of interstellar entities. Beyond these specific scientific discussions, 3A Atlas serves as an illustration of the dynamics of information management and public confidence. At the very moment NASA's Mars orbiters were strategically positioned to capture detailed imagery, perfectly timed to address critical questions about the object's nature, a governmental shutdown occurred. It is possible this timing was purely coincidental. Perhaps bureaucratic obstruction explains the absence of the images, but the visual impression is far from ideal. Individuals logically presume that organizations routinely managing intricate space missions possess the capability to facilitate image dissemination during shutdowns if they so choose. The prevailing perception, whether accurate or not, is that a deliberate decision was made regarding what information to release and what to withhold. Such perceptions foster speculative theories and erode public trust in institutional scientific communication. This issue is linked to a longer history of observations. The United States military operates satellites capable of capturing Earth's surface imagery with exceptional clarity. These capabilities are kept classified. The precise details of their observational capacity, their image processing techniques, and their areas of focus are all shielded behind security protocols. The rationale provided is national security, emphasizing the need to safeguard intelligence-gathering methods and prevent adversaries from comprehending our observational reach. However, this secrecy breeds suspicion about other withheld information. If certain space observations are classified for national security reasons, could others be classified for different motives? Should the government discover evidence of extraterrestrial technology, would it be publicly disclosed or kept confidential? The existing framework for classification is in place. The precedent for withholding space-related information has been established. Connecting these points, whether fairly or not, leads to assumptions of clandestine operations. Similar patterns emerge in other fields. When the Pentagon released unidentified aerial phenomena (UAP) videos in the year 2020, confirming that military pilots had encountered aerial phenomena that defied simple explanation, it corroborated claims that UFO enthusiasts had been making for decades. The government had in fact been tracking unexplained aerial objects and possessed footage that had not been previously released. In that particular instance, the conspiracy theorists who asserted that incomplete information was being provided to the public were proven correct. This does not imply that every speculative theory is valid. Most are not. However, it signifies that institutional credibility is diminished when agencies that previously dismissed certain subjects as nonsensical later acknowledge having taken those subjects seriously all along. This abrupt shift undermines trust. If their prior statements were inaccurate or misleading, why should present information be believed? 3 Atlas exists within this intricate context of trust, openness, and conjecture. It is plausible that it is merely a comet. Perhaps the anomalies are byproducts of incomplete observations and will dissipate as more data becomes available. It is possible that the missing NASA images will eventually be released, revealing entirely unremarkable surface features. Alternatively, something more unusual might be occurring, either with the object itself or with the way information pertaining to it is being managed. Without access to the comprehensive data, the public cannot independently assess these questions. They are dependent on institutional gatekeepers to disseminate information, provide context, and elucidate their findings. When these institutions fall silent at crucial junctures, individuals fill the void with speculation. Some of this speculation is rational, posing pertinent questions about the timing of observations and data accessibility. Other speculation is far-fetched, linking Three-Eyed Atlas to unrelated conspiracy theories concerning clandestine space programs and extraterrestrial encounters. The predicament for scientists operating within institutions is that transparency has limitations. Certain data necessitates meticulous calibration before its release, as raw observations can be misleading. Some information is restricted by international accords pertaining to satellite capabilities. Certain findings require peer review prior to public announcement to prevent the dissemination of premature conclusions. All of these represent legitimate grounds for delaying immediate disclosure. However, from an external viewpoint, these justifications can appear as pretexts. When anticipation mounts surrounding a discovery, when public interest reaches its zenith, and when everyone is eager to ascertain developments, being informed that data processing will take months can be perceived as obstruction. The existence of valid technical reasons for delays does not alter the emotional response. This inherent tension will not be resolved solely by 3-Atlas. It is a fundamental issue embedded within the operational framework of modern science, which functions within institutional structures possessing their own priorities, limitations, and risk tolerances. The scientific community prioritizes rigorous verification. The public values immediate transparency. Social media platforms reward speed over accuracy. Governmental agencies prioritize control over disclosure. These conflicting values frequently clash whenever contentious subjects emerge. What Three-Eyed Atlas signifies, beyond its specific characteristics as an interstellar object, is a test case for how we approach unusual observations in an era characterized by distributed information and institutional distrust. The conventional model, where experts issue pronouncements and the public accepts them at face value, has broken down. Individuals desire evidence, not merely conclusions. They wish to examine the data, conduct their own analyses, and form their own judgments. Amateur astronomers who download NASA's raw image archives and process them independently exemplify this shift. They are unwilling to await official releases and are disinclined to passively trust that experts will convey all significant information. They extract information from available data themselves. On occasion, their work uncovers details that official channels overlook. At other times, they commit errors that would have been avoided with superior calibration. Nevertheless, the impetus to verify rather than simply trust reflects broader cultural transformations concerning authority and expertise. Science has historically adapted to preceding cultural shifts. When the printing press facilitated wider knowledge dissemination, when public education expanded literacy, and when universities opened their enrollment beyond affluent elites, the scientific community modified its communication strategies. The current transition to social media and distributed information networks necessitates a comparable adaptation. Scientists must devise methods to uphold rigor and accuracy while operating within environments that incentivize speed and engagement. 3-Atlas will ultimately depart the solar system. By late the year 2026 or early 2027, it will have traversed Neptune's orbit and re-entered interstellar space. The observations will cease. The object will recede into the distance, becoming too remote and faint for our telescopes to track. Whatever knowledge we gain about it will be acquired before its disappearance. Subsequently, it will become another data point in databases, another reference for future researchers studying populations of interstellar objects. However, the questions that 3-Atlas prompts will endure. Inquiries regarding how we evaluate unusual observations. Questions about what evidence warrants extraordinary hypotheses. Questions concerning institutional transparency and public access to data. Questions about the operational methods of science within the contemporary information landscape. These are not purely abstract concerns. They influence societal decision-making across a spectrum of areas, from the prioritization of space exploration to research funding and science education. If Three-Eyed Atlas proves to be simply a comet, it will have nevertheless served a valuable purpose. It compelled these discussions. It illuminated the deficiencies in our observational capabilities, the limitations of our data release systems, and the challenges of conveying uncertainty to public audiences. These lessons extend beyond this single object. And if Three-Eyed Atlas is indeed something more than a comet, if observations from December or data from the JUICE mission reveal properties that cannot be naturally accounted for, then these conversations become even more critical. Humanity's response to confirmed evidence of extraterrestrial technology will depend in part on the trust established between institutions and the public. If individuals believe agencies are acting with transparency, a coordinated and thoughtful response can be orchestrated. If, however, people suspect cover-ups and concealment, the response risks becoming chaotic and divisive. We are approaching moments when these questions will be put to the test. Perihelion has passed or is passing as you listen to this. The object is situated behind the sun, engaging in whatever activities it pursues when unobserved. It will soon re-emerge. Telescopes will be directed towards it. Images will accumulate. Data will flow. Answers, or at least more refined questions, will be forthcoming. Regardless of the outcome, 3IE Atlas has already secured its place in astronomical history. It represents the third interstellar visitor, arriving at a time when our detection capabilities had just reached sufficient maturity to discern it, possessing characteristics peculiar enough to ignite serious scientific debate and enigmatic enough to capture the public's imagination. It journeyed from the vastness of space, carrying inquiries that we are still learning how to pose, let alone answer, and within a few weeks or months we will ascertain whether these questions have straightforward resolutions or whether they lead to uncharted territories that reshape our understanding of our position within this immense cosmic expanse, which we are only beginning to explore. The anticipation continues. The observational phase draws nearer. The narrative of Three-Eyed Atlas unfolds nightly across telescopes dispersed across our small planet. All of us watching collectively as this ancient wanderer traverses our transient abode. This brief convergence of trajectories in the void between celestial bodies